Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are drifting toward one of the strangest ideas ever allowed to sit politely at the edge of serious physics. Not a rocket that burns hotter and pushes harder. Not a spaceship that simply adds more engines, more fuel, and more ambition until the stars finally agree to come closer. Tonight, we are talking about the Alcubierre drive, a warp engine that, at least in the language of mathematics, seems to ask a very daring question. What if a ship did not have to move faster than light at all? What if space itself could be shaped in such a way that the destination came closer, while the place you left behind slipped farther away? It sounds like something whispered from science fiction, and in many ways that is where most of us first met the idea. A starship crossing impossible distances, a quiet command given on a bridge, a sudden leap, and the stars stretch into bright lines as if the night sky has been pulled like soft thread. It is a beautiful image. It is also, for anyone who has ever looked up at the real distances between stars, a deeply tempting one. Because space is not just large, space is almost rude about how large it is. The moon is already far enough to make the Earth seem fragile. Mars is so far away that even our fastest machines need months to get there. The nearest star beyond the sun is not waiting just over the hill. It is so distant that light itself, the fastest messenger we know, needs more than 4 years to cross the gap, and that is only the nearest one. So before we settle into the science, I would love to ask you something. Where are you listening from tonight? And if you could gently fold the space between your room and one place in the universe, where would you go first? Would you visit the rings of Saturn and watch them hang overhead like pale frozen roads? Would you drift above a quiet ocean world listening to the creak of ice under starlight? Would you go to a distant planet around another sun just to see whether its sunset has colours Earth has never invented? Or would you simply fold space across town, avoid traffic and arrive at the kettle before it has finished boiling? That last one may not sound as grand as interstellar travel, but on a rainy evening it has a certain practical charm. And if you find this journey soothing, or strange in a pleasant way, or just a quiet place to rest your thoughts for a while, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of calm science reach other tired travellers, people who may also want to wander through the universe without needing to pack a suitcase, check a launch window, or explain to anyone why they're watching a video about faster-than-light travel at 2 in the morning. I do hope tonight does not keep you awake with too much cosmic curiosity, but if it does, at least you will be lying there with a slightly better understanding of why the universe is both much stricter and much more imaginative than it first appears. So, settle in. Let the room become quiet. Let the ordinary world soften around the edges. Somewhere far above us, satellites are falling around Earth in careful curves. Farther away, planets are circling the sun with patient regularity. Beyond them, stars are scattered through the galaxy like distant lamps in a very large house. And between those stars lies the problem that has haunted every dream of deep space travel. The universe gives us places to imagine, but then places them behind distances so enormous that imagination arrives long before any engine could. To understand why the Alcubierre drive feels so astonishing, we need to begin with the simplest disappointment in all of space travel. The universe has a speed limit. It is not a speed limit printed on a sign at the edge of a highway. There is no cosmic police officer sitting behind an asteroid with a radar gun, although that would be a delightful use of public funding. The limit is woven into the structure of reality itself. According to Einstein's relativity, nothing with mass can be accelerated through space faster than light. Light does not merely travel quickly. It defines the upper edge of ordinary motion through space. It is the fastest way information, energy, or cause and effect can move from one place to another. That rule is not a minor inconvenience. It is the wall standing between human beings and the stars. Even if we built a spaceship far beyond anything we can build now, even if it could move at a respectable fraction of light speed, trips to other stars would still be measured in years, decades, or centuries. The galaxy is not arranged for impatience. It does not care that we would like to visit. It does not bend its scale around our lifetimes. A human life is warm, brief, and full of appointments. A galaxy is huge, cold, and very comfortable taking its time. This is why faster-than-light travel has such a powerful hold on the human mind. It is not only about speed, it is about refusing the loneliness of distance. It is about looking at a sky full of suns and not wanting them to remain forever, as little dots that make us feel poetic for a minute before we go back inside. It is about the hope that the universe is not just something we observe from one small planet, but something we might one day cross. The trouble is that physics, in its usual calm but firm manner, says no. You cannot simply push a ship faster and faster until it passes light. The closer a massive object gets to that speed, the harder it becomes to accelerate it further. The energy required grows beyond anything practical, then beyond anything imaginable, until the idea stops being engineering and becomes a very expensive way to argue with Einstein. And yet, physics has a funny habit of closing one door while leaving a window open just enough for someone curious to notice a draft. The speed limit applies to motion through space. It says a ship cannot locally race past a beam of light. But general relativity, Einstein's deeper theory of gravity, tells us something else as well. Space itself is not a fixed stage. It can stretch, it can curve, it can ripple, it can be warped by mass and energy. Gravity is not simply a force pulling objects around. It is the shape of space-time guiding how things move. The Earth orbits the Sun not because the Sun is tugging across empty nothing in a simple invisible line, but because the Sun curves the surrounding space-time, and Earth follows that curved path like a marble rolling along a smooth bowl. This is where the Alcubierre idea begins to take shape. If space-time can bend and stretch naturally around stars, planets, and black holes, then could it be arranged artificially around a spacecraft? Could space be compressed in front of the ship and expanded behind it? Could the ship remain safely inside a bubble of calm local space, never breaking the local speed limit, while the bubble itself carries it across enormous distances? In other words, could the universe be persuaded to move the road instead of forcing the car to break the rules? That is the quiet trick at the heart of the Alcubierre drive. It does not say the ship outruns light in the ordinary sense. It says the ship sits inside a region of space-time, a kind of warp bubble, while the space ahead contracts and the space behind expands. Imagine standing on a moving walkway at an airport. You're not sprinting. You might even be standing still, holding a small suitcase and wondering why airport carpets always look as if they were designed during a difficult decade. But the walkway carries you forward anyway. Now imagine the walkway is not beneath your feet but woven into space itself. That is not exactly what the Alcubierre drive is, but it gives the right feeling. The ship is not racing through local space faster than light. The geometry around it is doing something far stranger. This idea was proposed by the Mexican physicist Miguel Alcubierre in the 1990s. He was not building a secret engine in a mountain laboratory, or preparing to send a test pilot to Alpha Centauri by breakfast. He was exploring what general relativity allowed on paper. The result was surprising. The equations of general relativity seem to permit a space-time geometry in which a bubble could, in principle, travel faster than light relative to distant observers, while anything inside the bubble remained locally at rest. That phrase, in principle, is doing a great deal of work here. It is the scientific equivalent of saying, yes, the recipe exists, but it requires ingredients nobody has seen, a kitchen the size of Jupiter, and a chef who can bend reality without burning the soup. The most famous ingredient is exotic energy. To make the warp bubble work, the original Alcubierre model required a form of negative energy, something unlike ordinary matter and energy as we experience them. Ordinary matter attracts gravitationally. It curves space-time in familiar ways. Negative energy would curve space-time differently, in the strange manner needed to create and maintain the warp bubble. And here the dream becomes difficult. Negative energy is not something we can scoop into a fuel tank. It is not available by the barrel. There are subtle quantum effects that hint at tiny regions where energy can behave in unusual ways, but nothing remotely close to what would be needed for a starship. At least not with our current understanding. Still, there is something important about an idea that changes the question. Before Alcubierre, faster-than-light travel was usually imagined as simply going faster, as though the solution to the stars was a better engine and a stronger push. The Alcubierre drive shifted the focus. Maybe the real issue is not the ship's speed, but the shape of the space around it. Maybe the universe's rules are less like a locked door and more like a complicated contract, full of clauses that must be read very carefully. The speed of light remains a limit. Cause and effect remain guarded. But space-time itself has a flexibility that the older picture of the universe never allowed. This does not mean warp travel is close. It does not mean someone has a prototype humming gently in a desert hangar while a clipboard waits nearby. The Alcubierre drive remains highly theoretical. It has problems stacked on problems, and each one is large enough to make an engineer sit down quietly and stare into a mug of coffee. The energy requirements in early versions were absurdly high. Later refinements suggested they might be reduced, but reduced from absurd can still be rather unfriendly. The need for exotic matter remains unresolved. There are questions about stability, control, radiation, causality, and whether the people inside the bubble could even steer, start, or stop it once it existed. A warp bubble might be less like a vehicle and more like asking a thunderstorm to give you a lift and arrive neatly at the curb, and yet the idea refuses to disappear because it sits at that rare meeting point between imagination and real mathematics. It is not merely a fantasy of pushing buttons and leaping between stars. It comes from a serious theory, the same theory that explains black holes, gravitational waves, and the bending of light near massive objects. That gives it a peculiar kind of credibility. Not the credibility of something we can build tomorrow, more like the credibility of a strange map drawn at the edge of known territory. It may lead nowhere, it may lead to a cliff, or it may reveal that the landscape is bigger and more surprising than we expected. There is also a gentler reason the Alcubierre drive matters. It shows how science often begins not with certainty, but with a question that sounds almost childlike. What if we could go faster than light? A cautious person might answer, we cannot. A physicist might answer, not through space. Then another physicist might pause and say, but what about space itself? That little turn of thought is the engine behind many discoveries. Not ignoring the rules, but looking more closely at what the rules actually say. The universe is strict, but it is not always strict in the way our intuition expects. Our everyday intuition was formed in a slow world. We understand walking, throwing, falling, waiting, sleeping through alarms, and being mildly betrayed by train schedules. We do not naturally understand curved space-time, relativistic limits, or negative energy. The cosmos operates on scales and rules that feel strange because our brains evolved for forests, rivers, weather, food, and faces. So when an idea like the Alcubierre drive arrives, it feels impossible at first because it does not match the small local world our senses were built to handle. But the history of physics is full of ideas that once felt impossible. The Earth moving around the Sun, space and time being woven together, black holes from which light cannot escape, waves in space-time passing through Earth. Each one sounded odd before it became part of the furniture of modern science. The warp drive may never join that furniture. It may remain a beautiful mathematical curiosity, a reminder that equations can dream farther than engines. But even then, it is useful. It forces us to ask what motion really means. It makes us examine the difference between travelling through space and changing the shape of space. It invites us to think about the universe not as a hard, empty container, but as something active, responsive, and dynamic. Space is not simply the room in which things happen. It is part of the happening. Picture, for a moment, a small ship resting inside a clear bubble of calm. In front of it, the distance to a star is being squeezed, not by hands, not by metal, but by geometry. Behind it, the space it has crossed is expanding, widening like a wake left on a dark ocean. Inside, perhaps the crew feels no violent acceleration, no crushing force presses them backward into their seats. No engine roars in the ordinary sense. A cup of tea might sit safely on a table, which feels important, because any future of interstellar travel that does not protect the tea should be reconsidered carefully. Outside, distant observers might say the bubble is crossing space faster than light. Inside, the ship has not broken the local rule at all. It has taken advantage of the fact that relativity forbids one kind of motion, but allows space-time to behave in ways that are far less ordinary. Of course, between that picture and a real machine lies a canyon of unanswered questions. How would such a bubble be created? How would it be shaped? How would it avoid destroying anything in front of it? How would it stop at the destination without turning arrival into a cosmic incident? Could information from outside reach the ship while it travels? Could the crew choose where to go, or would they be sealed inside a moving pocket of space-time like a message in a bottle, thrown into a very complicated sea? These are not small details. They are the difference between a mathematical possibility and a technology. Science is full of possibilities that are real in theory but not in practice, like balancing every grain of sand on a beach into one perfect tower. The laws may not forbid it, but good luck finding the afternoon. Still, there is something comforting about allowing the mind to wander through such ideas slowly. We do not have to decide tonight whether warp drives will ever exist. We do not have to solve negative energy before sleep. We do not need to design a starship, file a patent, or explain to the neighbours why there is a small distortion in the driveway. Tonight, we only need to understand the shape of the question. The Alcubierre drive is not simply a fantasy about speed. It is a thought experiment about the flexibility of reality. It asks whether the vastness between stars is an absolute prison or a problem whose terms we have not fully understood. And that is where our journey begins, not with a finished engine, but with the rule that makes such an engine seem necessary in the first place. Before we can understand how a warp bubble might bend the road to the stars, we need to sit for a while with the universe's speed limit. We need to understand why light is so special, why ordinary motion cannot outrun it, and why the dream of crossing interstellar distances forced physicists to think not just about faster ships, but about the deep structure of space-time itself. The impossible speed limit written into the universe is not the sort of rule we first learn by looking at the sky. The night does not warn us. The stars do not come with little signs saying, "No faster than this, thank you very much." To the eye, space looks still and open, as if a determined enough ship could simply point itself toward a distant star and keep going until the distance gives up. That is how our everyday minds like to imagine motion. If walking is too slow, we run. If running is too slow, we ride. If riding is too slow, we fly. If flying is too slow, surely we build something louder, hotter, and more expensive, then strap ourselves into it with heroic optimism and a small packet of freeze-dried soup. Progress, at least in ordinary life, often feels like the art of going faster. But the universe is not ordinary life. It allows many strange things, but it is very particular about motion. It lets planets fall forever around stars. It lets black holes bend the paths of light. It lets time itself run differently depending on speed and gravity, which is a rather dramatic feature for something that also has to help us remember when to take the bins out. But when it comes to racing through space, the universe draws a line, not a rough guideline, not a polite suggestion, a deep rule built into the relationship between space, time, energy, and cause. And that line is the speed of light. Light moves so quickly that for most of human history people did not realize it moved at all. It seemed instant. Open your eyes and the world appears. Light from a candle crosses a room so quickly that the delay is beyond the reach of ordinary senses. A flash of lightning seems to arrive before the thunder only because sound is slow enough for us to notice its laziness. Light, by contrast, is the overachiever of the natural world. It does not stroll, it does not hesitate, it does not get distracted on the way. If light had a calendar, every appointment would be alarmingly punctual. Yet light is not infinitely fast. This was one of the great surprises in the history of science. The fact that light has a finite speed means that seeing is always looking into the past. When you look at the moon, you do not see it exactly as it is now, but as it was a tiny moment ago. When you look at the sun, you see sunlight that left its surface minutes earlier. When you look at the stars, you're seeing years, centuries, or even thousands of years into the past. The night sky is not a ceiling of present lights. It is an old archive shining quietly above us. Some of those stars may have changed by the time their light reaches us. Some may no longer exist in the same way. Space does not just separate places, it separates moments. This is where the speed of light begins to feel less like a speed and more like part of the structure of reality. It is not merely how quickly light happens to travel, it is the fastest speed at which information can pass from one place to another. It is the fastest speed at which one event can affect another. If something happens on a distant star tonight, we cannot know until the light or some other signal from that event reaches us. The universe does not allow the news to arrive early. It is very strict about delivery times, which is impressive, considering how large the address is. In Einstein's theory of relativity, this speed limit becomes unavoidable. Before Einstein, it was easy to imagine time as universal, space as fixed, and motion as something that simply added together. If you threw a ball while standing on a moving train, the ball's speed relative to the ground would depend on the speed of the train and the speed of your throw. That feels obvious. It is how most things behave at human speeds. But light refused to behave like an ordinary thrown object. Experiments showed that light's speed stayed the same for observers, no matter how they were moving. This was not a small inconvenience. It was a clue that our deepest assumptions about space and time were wrong. Einstein followed that clue with a sort of calm audacity that changes textbooks forever. If light speed is the same for everyone, then something else must adjust. Space and time themselves must be flexible. Moving clocks tick differently. Moving lengths are measured differently. Events that seem simultaneous to one observer may not be simultaneous to another. The universe preserves the speed of light by making space and time less absolute than they appear. That is a strange bargain, but reality seems very committed to it. This is why the speed of light is not like the speed of a fast car or a bullet or a spacecraft. It is woven into the way the universe keeps order. It sets the boundary for ordinary travel through space. It also protects causality, the simple but essential idea that causes come before effects. You knock a glass from a table and then it breaks. You do not hear the crash first and then decide to knock it over, unless you live in a very confusing kitchen. If information could travel faster than light in the wrong way, different observers might disagree about the order of events. In some situations, an effect could appear before its cause. Messages could arrive before they were sent. A person might receive a warning about a mistake they had not yet made, which sounds convenient until the entire logic of the universe starts quietly unraveling in the background. Causality is the hidden seriousness behind the speed limit. It is not just that the universe dislikes fast spaceships. It is that faster-than-light motion through ordinary space threatens the order that lets events make sense. The speed of light is like the stitching that keeps the fabric from tearing. Pull too hard in the wrong direction, and the pattern becomes strange. For objects with mass, the problem becomes even more stubborn. A spacecraft, a person, a speck of dust, or a biscuit crumb floating in the cabin all have mass. As something with mass is pushed faster and faster, more and more energy is needed to increase its speed. At low speeds, this is not obvious. A bicycle can go faster if you pedal harder. A car can accelerate with a stronger engine. A rocket can gain speed by throwing exhaust behind it with great enthusiasm and a regrettable amount of fuel. But as the speed of a massive object approaches the speed of light, the energy needed to keep accelerating grows without limit. The closer it gets, the harder it becomes to gain even a little more speed. Reaching light speed would require an impossible amount of energy, not merely a large amount, not the sort of amount that could be fixed with a bigger budget and a committee meeting. Truly impossible within the rules as we understand them. This is why light can travel at light speed and a spaceship cannot. Light is made of particles with no rest mass. They do not accelerate from stillness up to their speed like tiny glowing rockets. In empty space, light simply moves at that speed because of what it is. Matter is different. Matter cannot be pushed all the way to that boundary. It can get closer and closer in principle, but never arrive. The speed of light is like a horizon. You can travel toward it, but for anything massive it always remains out of reach. This creates the great heartbreak of interstellar travel. The nearest star system beyond our own is more than 4 light years away. That means light itself takes more than 4 years to cross the distance. Our fastest spacecraft would take far longer. A journey to even the closest neighbouring stars using ordinary propulsion could last thousands or tens of thousands of years, depending on the method. That is a long trip. Long enough that the first passengers might not live to see the destination. Long enough that their descendants might grow up knowing the ship better than any planet. Long enough that someone would eventually have to explain why the entire civilization is still arguing over who left a mug in the observation lounge. Science fiction often solves this by giving ships a faster-than-light drive. It is understandable. Without it, many space stories become less about exploration and more about extremely patient scheduling. But physics does not soften just because a story needs a brisker pace. If a ship moves through space, locally, like an ordinary object, it cannot outrun light. That is the rule. And it is this rule that makes the Alcubierre drive so interesting, because it does not try to win a direct race. To see the difference, imagine an ant crawling across a tablecloth. The ant can only crawl so fast. Its little legs have limits, and perhaps it has other ant responsibilities. If you wanted the ant to reach the far edge quickly, you could try to make it sprint, although motivating an ant is not an easy branch of engineering. Or you could move the tablecloth. If the cloth itself shifts, the ant can arrive at a new location without walking faster across the cloth. Its local speed remains perfectly ordinary, but the whole surface has carried it along. This is not a perfect picture of warp travel, because space-time is not a tablecloth in any simple sense, and ants are rarely involved in relativistic engineering. But the image helps. The Alcubierre idea asks whether a ship could remain at rest inside a small region of space, while the space around it changes shape. The key word is local. Relativity is very careful about local motion. Locally, nothing outruns light. In your immediate neighbourhood of space-time, light still defines the limit. A beam of light passing beside your ship would still move away from you at light speed. The ship inside a warp bubble would not feel itself accelerating beyond that boundary. It would not be blasting through nearby space like a reckless cosmic arrow. Instead, the bubble of space-time itself would be arranged so that space in front contracts and space behind expands. To a distant observer, the bubble might cross a large distance faster than light could have crossed the same distance through normal space. But inside the bubble, the ship has not violated the local rule. That distinction is subtle, but it matters enormously. The universe forbids one thing very clearly: massive objects moving faster than light through local space. It does not speak in quite the same way about the expansion or contraction of space itself. We already know space can expand. On the larger scales, the universe itself is expanding. Distant galaxies are being carried away from us as space between them and us grows. Very distant galaxies can recede from us faster than light, not because they are flying through space faster than light in a local sense, but because the space between us is expanding. This does not let us send messages faster than light. It does not break causality in the simple way a faster-than-light rocket might. It simply shows that the geometry of space has freedoms that ordinary objects do not. This is one of the strange lessons of general relativity. Space is not an empty, unmoving box. It is not just the stage on which matter performs. It can change, it can curve, it can stretch, it can ripple, as gravitational waves do when massive objects like black holes disturb the fabric around them. The universe is not a frozen room filled with moving furniture. The room itself can bend, and the furniture follows its shape. When we say the Alcubierre drive would warp space, we are speaking from this relativistic view, where geometry is physical. The shape of space-time affects motion, time, and the paths that objects can take. But before the dream becomes too comfortable, the speed limit returns with its stern little clipboard. Even if a warp bubble does not locally break the light speed rule, creating such a bubble may require conditions that are far beyond nature as we know it. The shape of space-time needed for an Alcubierre drive is not produced by ordinary fuel. You cannot simply burn hydrogen, push against empty space, and expect the universe to fold itself politely around the nose of your ship. The required geometry seems to demand exotic forms of energy, especially negative energy, arranged in extremely precise ways, and that is where theory begins to drift away from anything we can build. Still, it is worth appreciating why physicists take even the possibility seriously enough to study. General relativity is not a loose fantasy. It is one of the most successful scientific theories ever created. It has predicted and explained things that once sounded absurd. It told us that gravity bends light, and observations confirmed it. It implied the existence of black holes, and now we have evidence of them across the cosmos. It predicted ripples in space-time, and modern detectors have felt those ripples passing through Earth like faint tremors from distant collisions. So when general relativity permits a strange space-time geometry on paper, physicists do not immediately throw it away. They ask what it means. They ask what assumptions it requires. They ask whether the universe allows it physically or only mathematically, which is a very important difference. Mathematics can describe many possible shapes of space-time. Some are realistic, some are idealized, some may be impossible because they require matter or energy that cannot exist. The Alcubierre drive sits in this uncertain territory. It is a solution that appears within the framework of relativity, but it may demand impossible ingredients. It may also create deeper problems with horizons, radiation, and control. A warp bubble moving faster than light relative to distant space might have boundaries that behave in troubling ways. Signals from the front might not reach the ship. The crew might not be able to steer or stop the bubble from inside. It is one thing to imagine riding a bubble. It is another to discover that the bubble is less a vehicle and more a sealed envelope mailed through space-time by someone who forgot to include a return address. The speed of light also reminds us that the universe is not built around human convenience. That can feel discouraging at first, but it is also part of the beauty of physics. The rules are not made to flatter us. They are not adjusted to fit the length of a human life or the impatience of a curious species. They simply are. We discover them slowly, argue with them gently, test them carefully, and sometimes find unexpected loopholes that are not really loopholes at all, but deeper features of the same rule. The Alcubierre drive is fascinating because it does not deny relativity. It uses relativity. It tries to ask whether the same theory that imposes the speed limit also contains a hidden path around the kind of motion the limit forbids. There is a quiet humility in that. The dream of warp travel is not just a dream of power, it is a dream of understanding the rulebook well enough to notice the margins. A child might say, why not just go faster than light? A physicist answers, because massive objects cannot do that through space. Then comes the next question, softer but more interesting. What does through space really mean? If the distance itself can change, if space-time can be shaped, if expansion and contraction are not merely metaphors but real features of the universe, then the problem becomes stranger than speed. It becomes geometry. And geometry in relativity is not just the study of shapes on paper. It is the deep architecture of reality. The path of a planet, the falling of an apple, the bending of starlight near the sun, the slowing of time near a massive body, all of these are connected to the shape of space-time. The same theory that tells a clock to tick differently on a mountain than at sea level is the theory that lets us imagine a bubble carrying a ship by reshaping the space around it. That does not make the bubble practical. It does make it meaningful. Perhaps this is why the Alcubierre drive feels different from many science fiction inventions. It is not a magic engine painted with scientific words. It begins with a real limitation and a real theory. It respects the speed of light in the local sense, then asks whether the broader fabric of space-time can be made to do the travelling instead. It is a clever question. Maybe too clever for nature to permit, maybe not. Either way, it teaches us something. It shows that the speed of light is not just an obstacle, it is a guide. It forces our imagination to become more precise. It tells us that if the stars are ever to be reached quickly, the answer cannot be ordinary acceleration. It must be something stranger, something that works with the structure of the universe rather than trying to punch through it. So the impossible speed limit remains. It is still there, bright and firm, guarding the boundary of cause and effect. No ordinary ship can simply outrun a beam of light through local space. No engine can accelerate matter past that final threshold. But around that limit, general relativity leaves us with a universe more flexible than our instincts expected. Space can stretch. Time can bend. Distances can be shaped by gravity and energy. The road itself is not as solid as it looks, and once that thought settles in, the next step becomes almost irresistible. If a ship cannot break the speed limit, perhaps it can sit inside a moving pocket of space-time. If it cannot cross the galaxy by racing through space, perhaps it can ride a distortion of space instead. That is where Miguel Alcubierre enters the story, not with a finished machine, but with a mathematical bubble that changed the question from how fast can a ship move to how strangely can space itself be made to behave. Miguel Alcubierre did not begin by building a starship. There was no secret launch pad, no glowing engine hidden under a desert, no silver vessel waiting under a tarpaulin while someone in a lab coat whispered, "This should probably work." His contribution began in the quieter place where many strange revolutions in physics begin, inside a question. A question shaped not by metal, fuel, or wires, but by the mathematics of space-time. And the question was beautifully simple in its mischief. If relativity says nothing can move faster than light through space, what happens if the thing that moves is not the ship, but space itself? That is the turn that changed everything. It sounds almost too neat, as if someone found a loophole tucked into the back of the universe's instruction manual. But it was not really a loophole. It was more like reading the rule carefully enough to notice what it did and did not say. Einstein's relativity does not allow a massive object to locally outrun light. It does not allow a spaceship to simply push harder, accelerate faster, and win a race against a beam of light passing beside it. That part remains firm, but general relativity also says that space-time is not stiff. It can curve around mass, it can expand, it can contract, it can carry galaxies apart as the universe grows, it can ripple when black holes collide. If space-time has that kind of freedom, Alcubierre wondered whether it could be arranged in a way that makes a ship seem to cross vast distances faster than light, without the ship ever breaking the local speed limit. It's worth pausing over how unusual that kind of thinking is. Most of us, when we imagine reaching the stars, picture speed, better engines, bigger rockets, more fuel. A spacecraft roaring bravely into the dark, perhaps with a heroic soundtrack, and at least one person staring solemnly through a window. That is the natural human picture because it is how we move through the world. To get somewhere faster, we move faster. We do not usually ask whether the space between the living room and the kitchen can be persuaded to shrink. Although if it could, late-night snacks would enter a whole new era. Alcubierre's idea was different because it did not try to make the ship stronger than the speed limit. It tried to make the journey itself stranger. He proposed a shape of space-time that later became known as the Alcubierre metric. We do not need the mathematical details here, and thankfully nobody needs to tuck an equation under their pillow tonight. The essence is enough. Imagine a bubble surrounding a spacecraft. Inside that bubble, space is calm. The ship is not being crushed, stretched, or hurled forward by ordinary acceleration. It is resting locally, almost as if it were floating in a quiet pocket of reality. But outside the bubble, space-time is doing something dramatic. Space in front of the bubble contracts. Space behind the bubble expands. The ship does not cross the distance in the usual way. Instead, the distance itself changes around it. A familiar image is a surfer riding a wave, although even that is not quite right. The surfer moves through the water as well as with the water. A warp bubble would be stranger. The ship would ride a shaped region of space-time carried by the geometry rather than by motion through local space. Another image is a raisin in rising bread dough. As the dough expands, the raisins move apart, not because they're crawling through the dough, but because the dough between them stretches. Cosmologists use that kind of picture to describe the expanding universe. Alcubierre's idea turns the image into a kind of controlled distortion. Instead of letting the whole cosmic loaf rise everywhere, which is a phrase one should probably not say too often in serious company, imagine shaping the dough around one tiny region so that the region is carried along. The brilliance of the idea is that it obeys the local rule while seeming to bypass the large-scale obstacle. Inside the bubble, the ship is not moving faster than light relative to nearby space. A flashlight beam inside the cabin still behaves normally. A crew member can walk across the room without becoming a relativistic disaster. A cup of tea can remain on the table, which again feels like a minimum standard for civilized interstellar travel. Yet to someone watching from far away, the bubble could in principle cover a distance faster than a light signal, travelling outside the bubble through ordinary space. It would look like faster than light travel, but the trick would be that the ship is not doing the forbidden thing. The geometry is. This distinction is what made Alcubierre's proposal so fascinating. Before this, faster than light travel in serious physics was often associated with wormholes, hypothetical tunnels connecting distant regions of space-time. Wormholes are another strange gift from general relativity, though they come with their own enormous difficulties. Alcubierre offered something different. Not a tunnel, but a moving bubble. Not a shortcut through a throat in space-time, but a reshaping of the road itself. It was a clean, elegant idea, surprising enough that it entered both scientific discussion and popular imagination almost immediately. But elegant does not mean easy. In physics, an idea can be mathematically beautiful and still be physically troublesome, rather like a chandelier made of ice. Lovely to look at, but difficult to keep in the sitting room. The original Alcubierre drive required exotic matter or negative energy. This is not negative in the sense of being gloomy, badly behaved, or refusing to help with the washing up. It means energy arranged in a way that has unusual gravitational effects, the kind needed to warp space-time into the required bubble. Ordinary matter and energy curve space-time in familiar ways. Negative energy would curve it differently, allowing the expansion behind and contraction ahead that the drive needs. The problem is that negative energy is not something we know how to gather in large amounts. In quantum physics, there are tiny situations where energy can behave in ways that sound almost like negative energy. The Casimir effect is often mentioned here. It involves very small forces that appear between closely spaced surfaces because of quantum fields in the vacuum. This shows that the vacuum is not just empty nothing. It has structure. It can produce subtle effects. But there is an enormous gap between tiny quantum behavior in a laboratory and enough exotic energy to wrap a spacecraft in a bubble of warped space-time. That gap is not a puddle one can hop across. It is more like an ocean with fog on it, and possibly a sign reading, "Please reconsider." Early discussions of the Alcubierre drive suggested energy requirements so vast that they became almost comical. Not just more than a rocket could carry, not just more than a planet could provide. In some estimates, the amount was so enormous that it made the idea feel more like a cosmic joke played by mathematics. Later researchers found ways to modify the geometry and reduce the energy estimates. That sounds encouraging, and in a way it is. It shows that the original version was not the only possible version, but reduced from impossible does not automatically mean practical. If someone says the mountain has been lowered from infinitely tall to merely taller than anything in the solar system, you may still want to pack carefully. This is one of the reasons the Alcubierre drive lives in a strange category. It is not nonsense. It is not simply fiction. It arises from real relativity, but it is also nowhere near engineering. There is a large difference between saying that a mathematical spacetime can be written down and saying that nature allows you to build it, control it, power it, and use it to arrive gently around another star without turning the destination into a very brief warning story. Physics has many levels of permission. The equations may permit a shape. The universe may not provide the materials, or the shape may be unstable, or it may require conditions that create worse problems than the one it solves. The Alcubierre bubble asks to be taken seriously, but not casually. One of the deeper challenges is control. Suppose, just for the sake of imagination, that you could create a warp bubble. How would you start it? How would you steer it? How would you stop it? These are not small questions. A car has brakes because the car moves through a road and interacts with it. A ship at sea can turn because it pushes against water. An airplane can maneuver because air flows around it. But a warp bubble would be a distortion of spacetime itself. If the front of the bubble lies beyond the reach of signals from inside, the crew may not be able to affect what happens ahead. They might sit inside a calm region, but the very structure that lets the bubble travel faster than light, relative to distant observers, could isolate them from controlling the leading edge. That is less like driving and more like being inside a sealed lift after someone else has pressed a button labelled somewhere dramatic. There are also concerns about radiation and particles. Space is not perfectly empty. Even interstellar space contains stray atoms, dust, light, and radiation. A warp bubble moving across great distances might interact with these particles in dangerous ways. Some studies have suggested that energy could build up at the front edge of the bubble and be released when the bubble stops. If that release were intense, arrival might be less like gently entering orbit and more like making a very poor first impression on a new star system. Nobody wants humanity's first interstellar greeting to be apologies about the radiation burst. Then there is causality, the quiet guardian of cause and effect. Faster than light travel always makes physicists nervous because it can threaten the order of events. Even though the Alcubierre drive does not locally exceed light speed, its global faster-than-light behavior may still lead to situations where time loops or paradoxes become possible under certain arrangements. This is the sort of topic that makes the universe feel less like a tidy clock and more like a legal document written by a dream. If a warp bubble could be used to send signals or travelers in ways that violate causality, then either nature has some way of preventing it, or our understanding remains incomplete. Stephen Hawking once suggested the idea of chronology protection, the possibility that the laws of physics prevent time machines from forming. The phrase sounds wonderfully bureaucratic, as if the universe has a department specifically tasked with stopping reckless timeline behavior. Whether such a principle truly exists is still an open question. But the concern matters. Any faster-than-light concept must face not only engineering difficulty, but the deep logical structure of space-time. It is one thing to ask whether we can reach a star quickly. It is another to accidentally create a situation in which an effect tries to arrive before its cause, taps it politely on the shoulder, and asks why it is late. And yet, despite all these problems, the Alcubierre drive remains important because it changed the nature of the dream. It gave physicists a precise object to examine. Before Alcubierre, warp drives belonged mostly to storytelling. After Alcubierre, There was a mathematical model that could be studied, criticised, adjusted and challenged. That is a meaningful step. Science does not progress only by proving things possible. It also progresses by learning exactly why something is difficult or impossible. A clear impossibility is often more useful than a vague dream. It tells you where the walls are. It shows you what assumptions must change. It sharpens the question until the next person can ask it better. The history of physics is full of questions that sounded unreasonable before becoming central. What if time is not absolute? What if light behaves like both a wave and a particle? What if space itself can expand? What if empty space is not truly empty? Each question once had a scent of absurdity, not because people were foolish for doubting them, but because nature often hides its deeper rules beneath appearances that feel obvious. Time feels universal until relativity teaches otherwise. Empty space feels empty until quantum field theory fills it with restless activity. Gravity feels like a force pulling downward until general relativity reveals curvature. So when someone asks whether a ship might ride a bubble of space-time, the proper scientific response is not immediate belief and not immediate laughter. It is investigation. Alcubierre's proposal also reminds us that science fiction and science are not enemies. They're not the same thing, of course. A story can leap wherever it wants, while science must walk carefully through evidence and mathematics. But imagination can point toward questions that formal science later examines. Warp drives were imagined long before Alcubierre wrote his paper. Popular culture gave the idea a shape in people's minds. Then a physicist, familiar with the strange freedoms of general relativity, asked whether anything like that shape could exist mathematically. The answer was not yes in the practical sense. It was more like, under very strange conditions, something with a similar spirit can be described. That is a fascinating bridge between dreaming and reasoning. There is something very human about that bridge. We look at the stars and invent stories because the distances are too large for ordinary hope. Then science arrives and says, let us be careful. Let us check the rules. Let us find out what the universe actually permits. Sometimes science says no, and the dream must change. Sometimes it says yes, but not like that. Sometimes it says, strangely, the mathematics allows a door, but the handle may be made of something that does not exist. The Alcubierre drive belongs to that last category, which is perhaps why it is so difficult to stop thinking about. Miguel Alcubierre himself has often been careful about the idea. The proposal was not a claim that warp travel was around the corner. It was an exploration of general relativity's possibilities. That distinction matters. In popular discussions, the phrase warp drive can make it sound as though physicists are nearly ready to install one. In reality, the Alcubierre drive is a thought experiment at the edge of theoretical physics. It tells us more about the flexibility and strangeness of space-time than about the next generation of spacecraft. But sometimes that is enough. A thought experiment can reshape a field not by becoming a machine, but by forcing everyone to look at an old problem from a new angle, and the old problem remains enormous. Stars are far away. Human life is short. Ordinary propulsion is slow compared with cosmic distances. Even ambitious ideas such as nuclear pulse propulsion, fusion rockets, antimatter engines, or light sails pushed by lasers still face the tyranny of distance. They may one day send small probes to nearby stars within decades, perhaps, but crude travel across the galaxy remains in another category entirely. Without some way to deal with the light speed barrier, the galaxy stays mostly unreachable on human timescales. The Alcubierre bubble does not solve that problem practically, but it changes the emotional landscape. It says, perhaps the obstacle is not speed alone, perhaps distance itself is part of the question. That shift is profound. Imagine two islands separated by an ocean. One approach is to build a faster boat. Another is to discover that the ocean surface can be folded. If folding the ocean turns out to require impossible weather, mythical materials, and a very cooperative moon, then you have not solved travel. But you have learned that the map is not as simple as it seemed. In relativity, space-time is not a passive ocean. It is dynamic, it responds to energy, it shapes motion. Alcubierre's bubble is a way of asking whether that dynamism could ever be controlled rather than merely observed. There is also a philosophical softness to the idea. A warp drive in this form would not be about conquering space by brute force. It would be about cooperating with geometry. Instead of punching through the cosmic distance, the ship would ask spacetime to change its shape. That may sound fanciful, but physics has often advanced by learning not to fight nature directly. Aircraft do not defeat air. They use the behavior of air. Sailboats do not overpower the wind. They angle themselves to it. A warp drive would be the ultimate version of that principle, not overpowering the speed of light, but arranging space-time so the rule is respected locally while the journey becomes possible globally. Whether nature allows such cooperation is another matter. It may not. The negative energy problem may be fatal. Quantum inequalities may restrict exotic energy so severely that a practical bubble cannot form. Stability issues may make the concept collapse before it can carry anything. Causality may be protected by laws we do not yet fully understand. The Alcubierre drive may remain forever in the realm of mathematical curiosities, admired from a distance like a castle painted on a misty horizon. But even if that is its fate, it has already done something valuable. It has shown us that the question of faster-than-light travel is not simply about engines. It is about the nature of space-time itself. That is why the bubble changed the question. It moved the conversation away from how hard can we push a ship, and toward how deeply do we understand the stage on which motion happens. It asked us to think not only about velocity, but about geometry. Not only about fuel, but about energy conditions. Not only about reaching the stars, but about the rules that decide what reaching means. And once that question is in the room, it quietly rearranges everything. So picture the Alcubierre bubble again, not as a finished spacecraft, not as a promise, but as a thought held carefully in the mind. A small island of calm surrounded by a storm of geometry. Space ahead drawn inward, space behind pushed outward. The ship inside neither racing nor breaking the local law, but being carried by a shaped distortion of the universe's own fabric. Around it lies every difficulty we have named: exotic energy, control, radiation, causality, stability, and the small inconvenience of not knowing whether any of this can exist outside mathematics. Still, the image remains. It remains because it speaks to the same part of us that once looked at birds and imagined flight, looked at the moon and imagined footprints, looked at the atom and imagined hidden worlds. Not every dream becomes a machine, but some dreams become better questions. Miguel Alcubierre gave physics one of those questions, and to understand it more clearly, we have to step inside the bubble itself, not with a wrench or a helmet, but with careful imagination, and ask how a ship could move without really moving in the ordinary sense. To understand how a warp drive could move without really moving, it helps to forget engines for a moment. Forget flames, rockets, roaring exhaust, shaking metal, and all the usual drama we associate with getting somewhere quickly. A normal spacecraft moves by pushing something backward so the craft is pushed forward. It throws mass behind it, or catches light, or uses gravity, or follows a careful path through the solar system like a patient billiard ball. Every ordinary method of travel shares the same basic idea. The vehicle changes its motion through space. It accelerates. It crosses distance. It has a speed measured against the space around it. And because it is moving through local space, it has to obey the local speed limit. A warp drive changes the feeling of the question. It does not begin by asking how hard the ship can push. It asks whether the distance itself can be handled differently. That is the strange heart of the Alcubierre idea. The ship does not become a bullet fired faster than light. It does not slice through the universe at forbidden speed, leaving physics coughing politely behind it. Instead, the ship rests inside a region of space that is carried along by a distortion of the surrounding geometry, The motion belongs less to the ship and more to the shape of spacetime around the ship. It is not speed in the usual sense, it is travel by rearrangement. This is where our everyday language begins to struggle. We say the ship moves because from the outside it changes location. It begins near one star and ends nearer another. If the journey happens quickly enough, an observer far away might say the ship has crossed the distance faster than light would have done in ordinary space, but inside the bubble, the ship may not be moving much at all relative to its immediate surroundings. The cabin is not racing through local space. The chairs, walls, instruments, and probably the half-forgotten mug near the control panel are all sitting inside the same calm pocket. A crew member could float gently down a corridor, pour tea if they were brave, and not feel the crushing force that would come from ordinary acceleration to impossible speeds. That is the first deeply odd point. A warp drive is not supposed to shove a ship faster and faster until it reaches light speed. That route is closed. The energy required would rise without limit, and the ship could never cross the boundary. The Alcubierre drive imagines a different route. It surrounds the ship with a bubble of space-time. Inside that bubble, conditions are normal enough for the ship to remain at rest. Outside the bubble, space itself is shaped so that the region ahead shrinks and the region behind expands. The destination is not reached because the ship rushes through every meter between here and there in the usual way. It is reached because the geometry between here and there changes. A simple image is a rug on a polished floor. Suppose a toy boat sits on the rug. If you drag the toy boat across the rug, the boat moves relative to the rug. That is ordinary travel. But if you pull the rug itself, the boat comes along even if it remains still on the fabric. The toy has changed location in the room, but not because it drove across the rug. The surface carrying it changed position. Now, spacetime is not a rug, and a starship is not a toy boat, and dragging the universe across the floor is not usually recommended before bedtime. Still, the image catches the basic shift. The ship does not outrun light across the local surface. The surface is altered. Another picture is a surfer on a wave, though again, the comparison is imperfect. The surfer is carried by water that is already moving. In the Alcubierre idea, the bubble is more like a wave in space-time itself, a shaped disturbance that can carry a quiet interior. The ship is not forcing itself through the ocean. It is sitting inside a crest of geometry. The front of the bubble pulls space inward. The back of the bubble pushes space outward. The ship in the middle rides the changing distance like a passenger in an elevator whose building is being politely rearranged around it. The word bubble is useful because it suggests a boundary. Inside the boundary is the local region of the ship. Outside the boundary is the rest of the universe. The wall of the bubble is where the strange shaping occurs. Space in front is compressed. Space behind is expanded. The center remains comparatively gentle. If this could be done, the ship would not feel the brutal acceleration of a normal craft trying to reach extraordinary speeds. That matters because acceleration is not just a number on an instrument. It is something bodies feel. It presses, strains, and damages. A human being cannot simply be accelerated to extreme speeds instantly and remain a human being in any comfortable sense. The warp bubble avoids that by making the ship locally calm while the surrounding space-time does the hard work. This leads to a wonderfully strange phrase often used in explaining the idea. The ship moves without moving. Of course, it does move in the everyday sense that it gets from one place to another, but it does not move through nearby space in the forbidden way. It is not locally faster than light. It is not racing past light beams beside it. If a beam of light were shining inside the bubble, it would still behave like light normally behaves. The ship has not defeated light in its own neighborhood. It has changed the neighborhood. That local neighborhood is crucial in relativity. The laws of physics, as experienced in a small enough region of space-time, remain consistent. You cannot perform a simple experiment in your sealed cabin and discover that you are breaking the light speed limit through local space, because inside the bubble you are not. This is the cleverness of the proposal. It respects the rule where the rule is strictest. It does not ask matter to do what matter cannot do. It asks space-time to take on a shape that produces an unusual global result. The difference between local and global can feel slippery, so let's approach it slowly. Imagine walking inside a train. Relative to the train, you move at a comfortable walking pace. Relative to the ground outside, your motion includes the train's motion too. You have one local speed and another larger speed when seen from a different frame. Now take that idea and make it far stranger. In a warp bubble, the ship's local motion can be small, but the bubble's position relative to distant places can change dramatically because the geometry between those places has changed. The ship is not simply adding its speed to something else. The very measurement of distance and time has been shaped. This is why the Alcubierre drive belongs to general relativity rather than ordinary mechanics. In ordinary mechanics, space is the stage, and objects move across it. In general relativity, the stage can flex. The stage can curve. The stage can become part of the performance. Gravity is already an example of this. A planet does not orbit because a mysterious hand pulls it around in a circle. In Einstein's view, it follows a curved path through curved space-time. The shape guides the motion. A warp drive would be an attempt to shape space-time deliberately, not just let stars and planets shape it naturally. Nature already expands space. The universe as a whole has been expanding for billions of years. Distant galaxies are not necessarily flying through space like sparks from a fire. Much of their separation grows because space between them expands. Very far away, galaxies can recede from us faster than light because the space between us and them is stretching. This does not mean they are breaking the local speed limit. It means cosmic expansion is not the same as ordinary motion through space. The Alcubierre idea borrows that deep lesson. If space can expand naturally, perhaps a region of space could, in principle, be made to expand behind a ship and contract ahead of it. That phrase "in principle" deserves a soft little warning bell. In principle is not the same as in the garage by Thursday. It means the mathematics can be written in a way that describes the possibility under certain assumptions. It does not mean the universe gives us the materials, the method, or the safety manual. The warp bubble is like a sentence that grammar allows, but reality may refuse to pronounce. Still, the sentence is meaningful enough to study. The ship inside the bubble would experience something like stillness, at least in the ideal picture. This is one of the most appealing features. Ordinary high-speed travel creates severe issues. The faster you go, the more energy you need. The more you accelerate, the more stress the crew feels. Even if you somehow reached a huge fraction of light speed, striking tiny dust grains would become dangerous because relative speeds would be enormous. A warp bubble does not remove every danger, not even close, but it changes which problems dominate. The crew is no longer trying to survive impossible acceleration. The challenge becomes how to create and control the bubble, how to protect it, and how to arrive without causing trouble on a truly cosmic scale. There is also a quiet difference in how time might be experienced. In ordinary near-light speed travel, time dilation becomes central. A ship moving extremely fast through space would experience time differently than observers at rest. The crew might age less than people back home. That is real physics, and it is one possible way of reaching the future. But the warp idea tries to avoid needing the ship itself to move at near light speed locally. The bubble's strange global motion would not simply be the same as an ordinary relativistic flight. The details are complicated, and different versions of warp concepts raise different questions. But the key point is that the ship is not supposed to be a normal high-speed object. If all of this sounds too neat, that is because we have been describing the dream version. The difficulties arrive quickly. A bubble like this would require energy arranged in extremely unusual ways. It is not enough to curve space-time a little. Earth curves space-time, the sun curves space-time, even you curve space-time by a tiny amount, though perhaps not enough to impress anyone at dinner. But the Alcubierre bubble requires a very particular pattern of curvature. The front must contract, the back must expand, and the boundary must maintain a stable shape around the ship. Ordinary matter and energy do not seem able to create this pattern. The original idea required negative energy, a strange kind of energy density that may exist only in tiny quantum situations and not in the vast controlled amounts needed for travel. This is why no one is quietly testing a warp drive in orbit. The mathematics is far ahead of the engineering. Actually, it may be far ahead of what nature allows at all. To build the bubble, one would need to manipulate space-time directly with exquisite precision. That means not only having enough energy, but placing it in the right configuration around the ship. Imagine trying to hold a soap bubble in a perfect shape during a hurricane, except the soap bubble is space-time, and the hurricane is every unsolved problem in theoretical physics. It is a charming image, but not a comforting engineering plan. Then there is the issue of communication and control. If the bubble is moving faster than light relative to distant space, parts of it may become causally separated from the ship inside. That means signals from the crew might not reach the front boundary. If you cannot influence the front edge, steering becomes a very awkward concept. Starting the bubble may require arranging space-time ahead of the ship before the journey begins. Stopping may require conditions at the destination. In some interpretations, the crew might ride the bubble but not command it from within. That turns the warp drive from a spaceship into something more like a prepared path, a moving corridor whose controls are not where the passengers are sitting. That is a very different dream from the familiar Starship bridge, where someone points and says onward, and the universe respectfully stretches. A real warp system, if one could exist, might need infrastructure. It might require external fields, prepared routes, or devices at both ends. It might not be a free-roaming engine at all. Of course, this is speculation layered upon speculation, but it shows how careful we must be. The phrase warp drive makes us imagine a self-contained machine. The physics may point instead towards something stranger and less convenient. There is also the problem of what the bubble meets as it travels. Interstellar space is thin, but it is not empty. There are particles, dust grains, radiation, magnetic fields, and light. A warp bubble moving across vast distances could gather or disturb these things at its leading edge. Some analyses have suggested that dangerous radiation could accumulate and then be released when the bubble slows or stops. If so, arrival might be hazardous not only for the crew, but for whatever lies ahead. A drive that gets you to another star but announces your arrival by blasting the neighbourhood is not exactly the gentle ambassador humanity might hope for, so the image of moving without moving must be held carefully. It is not a magic trick that solves everything. It solves one problem by opening many others. It avoids the direct breaking of the local light speed limit, but it demands a command of space-time that is wildly beyond us. It offers a possible shape of travel, but not the ingredients or the workshop. The ship may rest in its bubble, but the bubble itself is a storm of physical requirements, and yet, this is what makes the idea so interesting. It shows that motion is deeper than our everyday sense of it. We think of travel as crossing distance. Relativity teaches that distance itself depends on the shape of space-time. We think of speed as the main issue. The Alcubierre drive suggests that geometry may be just as important. We think of a spaceship as something that moves through the universe. This idea asks whether a spaceship could be carried by a deliberate change in the universe's structure. There is a peaceful strangeness in that. The ship is not a spear thrown at the stars. It is more like a seed carried in a fold of the cosmic fabric. It does not conquer the distance by force. It changes the meaning of the distance, at least in the idealized mathematics. Ahead, the path becomes shorter. Behind, the space already crossed grows longer. In the middle, the ship remains in its little island of calm. It is a bold image, but also oddly quiet. No roaring engines are required in the picture, no heroic shaking, just a controlled distortion of space-time, which is somehow both more elegant and much more alarming. The phrase moving without moving also invites a deeper question. What does it mean to be at rest? On Earth, rest feels simple. You sit in a chair, the chair sits on the floor sits on the planet, and the planet quietly spins and orbits the sun while the sun circles the galaxy. So perhaps rest was never as simple as it felt. Motion always depends on what you measure it against. Relativity takes that lesson further. There is no universal stillness. There are local frames, observers, paths, and relationships. The Alcubierre bubble plays with this idea at an extreme level. Locally, the ship can be still. Globally, it can arrive somewhere else faster than expected. The conflict is not a contradiction. It is a sign that spacetime is not merely background scenery. This is where the Alcubierre drive becomes more than a science fiction flavoured curiosity. It becomes a lesson in how reality is described. The universe does not keep a single simple ledger of motion in the way our intuition wants. It has local rules and global structures. It has paths shaped by curvature. It has distances that can grow because space expands. It has time that can slow near mass or at high speed. Once all of that is true, a warp bubble becomes a natural question to ask, even if the answer turns out to be no. It asks whether the flexibility of space-time can be organised into travel. For now, the answer is not a practical yes. It may never be. The negative energy problem may remain impossible. Quantum laws may forbid the needed arrangement. Causality may block the route. The bubble may be unstable, uncontrollable, or dangerous. But the concept still performs a useful service. It separates faster than light travel into two different ideas. One is forbidden, a massive ship racing locally through space faster than light. The other is more subtle, a shaped space-time carrying a region in a way that changes distances without local violation. The first is a locked door. The second is a strange drawing of a door, with a note attached saying, "No handle found yet." And maybe that is enough for this stage of the journey. Science often advances by drawing such doors. Some vanish under scrutiny, some reveal hidden walls, a few become real entrances. The Alcubierre drive has not opened interstellar space, but it has opened a way of thinking. It has made the problem of cosmic distance feel less like a demand for bigger engines and more like an invitation to understand space-time itself. It asks us to imagine a ship that does not win a race against light, but rests inside a bubble where the race has been redefined. So when we say a warp drive could move without really moving, we mean that the ship would not be moving through local space in the ordinary forbidden way. The bubble would change the geometry around it. Space ahead would contract. Space behind would expand. The ship would remain in the middle, carried by the distortion, quiet inside a region of ordinary local physics while the universe outside does something extraordinary. That middle region is where the idea becomes easiest to picture and hardest to build. It is the calm eye of a storm made not of wind, but of warped space-time. And to understand why the bubble has that shape, we need to look more closely at the three parts of the picture: the space in front, the space behind, and the strangely peaceful ship between them. Now picture the warp bubble as gently as possible, not as a roaring machine, not as a bright tunnel full of sparks and dramatic alarms, but as a carefully shaped region of space-time with three important parts. There is the space in front of the ship, the space behind the ship, and the ship itself resting in the middle. That sounds almost too simple, like describing a sandwich and accidentally discovering interstellar travel. But this arrangement is the heart of the Alcubierre idea. The ship is not supposed to smash through the distance ahead of it. The distance ahead is supposed to become smaller. The ship is not supposed to leave ordinary space behind in the usual way. The space behind is supposed to expand. And between those two strange motions sits a quiet pocket where the spacecraft remains locally calm. This is the image that makes the Alcubierre drive so different from a normal engine. A rocket points in a direction and accelerates through space. A warp bubble reshapes the space around the rocket. It does not treat the universe as a fixed hallway that must be crossed step by step. It treats space-time as something with texture, something that can, at least in theory, be compressed and stretched. The ship in the middle is almost the least dramatic part of the picture, which is amusing because in most space travel stories the ship gets all the attention. We name it, polish it, give it a proud silhouette against a planet, and place heroic people at its windows. But in the Alcubierre picture, the ship is more like a passenger inside a moving region. The real actor is the geometry around it. Start with the space in front. If the destination is far away, the ordinary solution is to travel across the distance. But the warp idea asks whether that distance can be shortened by contracting the space ahead. This does not mean pulling the star closer like a bead on a string. It does not mean dragging planets around or rearranging the galaxy like furniture before guests arrive. It means altering the measure of space between the bubble and what lies ahead. In the language of general relativity, distances are not always as rigid as they seem. Gravity can change the geometry of space-time. The expanding universe can increase the space between distant galaxies. So the Alcubierre idea imagines using that flexibility in a controlled, highly localized way. A gentle analogy is a folded map. If you want to move from one side of a paper map to the other, you could trace the long path with your finger, or you could fold the paper so the 2 points come closer. The finger has not travelled faster across the surface. The surface itself has changed its arrangement. Of course, real space is not a paper map, and folding space-time is not something you can do on the kitchen table next to the biscuits. But the analogy gives a hint. Contracting the space in front of the bubble would make the destination effectively closer, at least from the point of view of the bubble's path. This front contraction is not like ordinary compression of air or water. When you squeeze air into a smaller volume, pressure rises. Molecules crowd together. Something physical is being packed more tightly. With space-time, the idea is stranger. You're not squeezing a substance in the usual sense. You're changing the geometry that defines separation. Space is not a material like foam, though we often use stretchy images because our brains like something they can imagine holding. It is better to think of space-time as the set of relationships that tell objects how far apart they are, how clocks tick, and what paths are natural. Changing that geometry changes the journey. In front of a warp bubble, space would be shaped so that the region between the ship and the destination narrows in a mathematical sense. The bubble does not need the ship to move through every bit of that distance in the usual way. The road ahead is shortened. A traveller inside might not feel any sudden rush. They might not be thrown backward in their chair. If the bubble were ideal and stable, the local environment could remain peaceful, while the front boundary performs the impossible-looking work of making the path ahead smaller. It is a calm centre surrounded by extraordinary geometry, like sitting in a quiet room while the hallway outside is being rearranged by a very ambitious architect. Behind the ship, the opposite happens. Space expands. This expansion is not merely the ship leaving a trail in the way a boat leaves a wake. A boat pushes through water and disturbs it. A rocket moves through space and leaves exhaust, radiation, and occasionally a great deal of paperwork. A warp bubble would not simply leave disturbed space behind because of the motion. In the idealized Alcubierre model, the expansion behind is part of the engine itself. Space behind the bubble grows, helping carry the bubble away from its starting point. This rear expansion is just as important as the front contraction. The ship is not only being drawn toward a shortened path ahead, it is also being separated from where it was. In the moving walkway analogy, the walkway behind you is moving away, while the path ahead comes toward you. In the rising bread analogy, the dough stretches and carries embedded raisins apart. For the warp bubble, expanding space behind means the origin falls away, without the ship having to speed through its local region. The bubble rides a gradient of geometry, with contraction in front and expansion behind. It is tempting to imagine the space behind swelling like a balloon and pushing the ship forward. That image is not completely useless, but it can mislead. The ship is not being shoved by a physical wall of expanding space in the way wind might push a sail. It is more subtle. The bubble's geometry is arranged so that the region containing the ship changes its position relative to distant points. The expansion behind and contraction ahead are parts of one space-time shape. They work together to make the bubble advance. If the front alone contracted, the picture would be incomplete. If the back alone expanded, also incomplete. The motion comes from the whole arrangement, and then there is the ship in the middle. This is the calm eye of the warp bubble. In the ideal picture, the spacecraft sits inside a flat, or nearly flat region of space-time. That means the crew would not be stretched apart by tidal forces or crushed by acceleration. They would not need to endure the kind of forces that would normally come with reaching absurd speeds. Inside, the ship is not locally exceeding the speed of light. The bubble may change position relative to distant stars at a faster than light rate, but the ship itself is not racing through its immediate surroundings faster than light. The crew could, in principle, experience ordinary physics around them. This middle region is essential because it is what protects the idea from the most obvious objection. If a ship with mass cannot move through space faster than light, then the ship must not do that. The bubble must carry it while preserving local rules inside. A flashlight in the cabin should still behave as a flashlight. A falling pen should still drift or fall depending on the ship's artificial gravity, assuming anyone in the future still uses pens. Conversations should still happen in order. Tea should still cool, although perhaps more slowly if the future has finally solved that particular tragedy. The ordinary world inside the bubble remains ordinary enough for life and instruments to function. This is also why the phrase warp bubble is more than decoration. A bubble separates an inside from an outside. Inside, the ship rests in a region of normality. Outside, space-time is curved and shaped intensely. The boundary is where the strange things happen. This boundary would not be a wall made of metal or glass. It would be a region of altered space-time geometry. Crossing it or interacting with it might be extremely dangerous or impossible depending on the details. It would be less like the transparent dome of a greenhouse, and more like a mathematical frontier between calm local physics and a storm of curvature. If you were inside such a bubble, what would you see? That is not an easy question. Popular images often show stars stretching into lines, as if the ship is racing forward through a cosmic rainstorm. But a true warp bubble might distort light in more complicated ways. Light from ahead and behind could be shifted, bent, concentrated or blocked depending on the bubble's structure. The crew might not have a simple window view at all. They might not be able to receive normal signals from the direction of travel. Their universe could become strangely enclosed. The dream of standing at a window watching stars slide by may be replaced by instruments struggling to interpret a space-time boundary that does not behave like ordinary empty space. This leads to one of the unsettling control problems. If the ship sits inside the bubble and the bubble's front boundary is causally difficult to reach, how does the crew steer? If signals cannot travel from inside to the front edge fast enough or at all under certain conditions, then the people in the middle might not be able to command the very distortion that carries them. A normal vehicle puts the driver inside the vehicle. A warp bubble may require the important controls to be arranged outside before the journey begins, or perhaps at the destination, or perhaps through some structure we have not imagined. This is where the cozy picture of a starship bridge becomes less certain. A warp ship may not be like a car at all. It might be more like a train running on a track made of prepared space-time, except the track is invisible, theoretical, and possibly impossible. The space in front also raises another problem. If the bubble contracts what lies ahead, what happens to particles, dust, and radiation in its path? Interstellar space is thin, but it is not empty. There are atoms drifting between stars. There are photons travelling from every direction. There are tiny dust grains that can become dangerous at high relative energies. If the warp bubble interacts with this material, it might gather energy near the front. Some studies suggest that particles could pile up or become blue-shifted, meaning their energy increases from the bubble's perspective. When the bubble stops, that accumulated energy might be released. This is the sort of detail that turns a beautiful idea into a very cautious one. Arriving at another star is less impressive if the arrival produces a burst of radiation strong enough to make nearby planets reconsider their hospitality. The space behind brings its own strangeness. Expanding space sounds gentle because we associate expansion with the universe itself, slow and vast, carrying galaxies apart over cosmic time. But in a warp drive, expansion would be concentrated and controlled behind a small bubble. That is not something nature normally does for our convenience. To make it happen, energy would need to be distributed in a very specific way. The original Alcubierre idea requires negative energy density in the bubble wall, a kind of exotic condition that ordinary matter does not provide. The front and back are not just shapes drawn on a diagram. They are demands placed on the physical universe, and the universe, as we have learned, is not always generous with exotic ingredients. This is why the bubble cannot be separated from its energy problem. The front contraction, the rear expansion, and the calm middle are not three pieces you can assemble with ordinary machinery. They are aspects of a single spacetime geometry. To create that geometry, you need a stress and energy arrangement that tells spacetime how to curve. In general relativity, matter and energy shape spacetime. If you want spacetime to take on a very unusual shape, you need very unusual matter or energy. This is the point where the dream begins to ask for things that may not exist in useful amounts. Negative energy is not stored in tanks. It is not mined from an asteroid. It does not appear on a hardware shop shelf between batteries and rope, though that would certainly make weekend projects more interesting. There are tiny quantum effects that suggest the vacuum can behave in strange ways. Empty space is not perfectly empty in modern physics. Quantum fields fill it, and under certain conditions, small negative energy-like effects can appear for brief and limited situations. But using that to build a warp bubble is like noticing that a candle flame flickers and concluding that you can use it to move a continent. The fact that nature permits a hint of something does not mean it permits the grand version required by an interstellar engine. The scale and control needed are beyond anything we know. Still, the three-part shape remains powerful because it teaches the core idea clearly. Contract in front, expand behind, rest in the middle. This is the entire dream in a simple sequence. The ship does not push across space. The geometry around it changes the effective journey. The front reduces the distance to the destination. The back increases the distance from the origin. The middle preserves the ship in a local region where the speed of light remains undefeated. It is elegant enough to be memorable and difficult enough to remain safely theoretical. There is something almost peaceful about the ship in the middle. It is not straining. It is not burning oceans of fuel. It is not fighting the speed of light with brute force. It sits in a pocket of calm while the universe is asked to do something subtle and enormous around it. That contrast is part of the beauty of the idea. The center is quiet because the boundary is extreme. The traveller rests because the road changes. In a way, it is the opposite of ordinary travel. We usually accept that the world is fixed, and we must do the moving. The Alcubierre drive imagines the traveller nearly still while the world around the traveller is rearranged. This also makes the idea feel oddly connected to the deeper lessons of relativity. Relativity has always told us that motion is not absolute in the simple way we imagine. Observers moving differently disagree about time and distance. Clocks tick at different rates depending on speed and gravity. Space and time are not separate, rigid backgrounds. They are woven together into a dynamic structure. The warp bubble is an extreme thought built from that same cloth. It says, if space-time is flexible, then maybe travel is not only a matter of crossing distance. Maybe it is also a matter of shaping distance. But shaping distance is not the same as escaping consequences. Every change in space-time must come from something. Every curve has a source. Every dramatic geometry asks a physical price. The front, the back, and the middle may sound like a simple arrangement, but each piece hides a difficulty. The front must contract without destroying the path ahead. The back must expand without requiring impossible energy. The middle must remain stable and safe. The boundary must not trap, blind, or irradiate the crew. The whole bubble must start, move, and stop without tearing causality into a philosophical scarf. So when people ask whether the Alcubierre drive is possible, the honest answer is layered. As a mathematical idea within general relativity, a warp bubble can be described. As a physical machine, it remains far beyond known science, and perhaps forbidden by deeper rules we do not yet fully understand. The three-part picture gives the concept its charm, but also reveals its burden. The same geometry that makes it fascinating makes it difficult. The same bubble that protects the ship demands exotic conditions at its edge. The same contraction and expansion that suggest faster than light travel also raise questions about control, safety, and causality. And yet, this is exactly why the idea matters. It forces us to think clearly about what travel means. It teaches that the distance between stars is not merely a number on a map, but a feature of space-time. It reminds us that speed is not the only way to imagine motion. It also shows how carefully science separates an allowed equation from a buildable engine. The Alcubierre bubble is not a promise that humanity will soon cross the galaxy. It is a question with a shape. A front that contracts, a back that expands, and a middle where a ship waits quietly, as if the universe might one day learn to carry it. For now, that ship remains in the realm of thought. It rests inside a bubble drawn by mathematics, not metal. The space in front of it is shortened by imagination guided by relativity. The space behind it widens in the same careful dream. The middle stays calm because the ship itself is not being asked to outrun light. Around the bubble, all the hard questions gather. What kind of energy could do this? How much would be needed? Could negative energy ever be controlled? Could the boundary stay stable? Could the crew survive the journey and choose the destination? Those questions lead us away from the simple picture and toward the strange price of bending reality, where the dream of a warp engine meets the unsettling demand for exotic energy, negative mass, and forms of matter that may exist only as faint whispers in the deepest corners of physics. The moment we begin asking how to bend space-time on purpose, the dream becomes expensive in a way that is difficult to overstate. Not expensive like a new telescope, or a lunar mission, or a kettle that claims to be smart and then still only boils water. Expensive in the deeper physical sense. A warp bubble is not something that appears because a ship has a powerful engine bolted to the back. It is a shaped region of space-time, and in Einstein's universe, space-time does not change shape for free. Matter and energy tell it how to curve. If you want a gentle curve, a planet can provide one. If you want a violent curve, a star or black hole will happily demonstrate, though preferably from a safe distance. But if you want the very specific shape needed for an Alcubierre drive, with space contracting in front, expanding behind, and remaining calm in the middle, then the universe seems to demand something far stranger than ordinary fuel. This is where exotic energy enters the room, usually wearing a suspiciously interesting hat. Exotic energy is not simply a more advanced version of rocket fuel. It is not a brighter flame, a denser battery, or a futuristic crystal glowing in the engine bay, because the design team thought it looked dramatic. In this context, exotic means energy or matter with unusual properties, properties that ordinary matter does not seem to have. The original Alcubierre model required a kind of negative energy density. That phrase sounds almost harmless at first, as if the energy has simply had a gloomy day. But in physics, it points towards something much deeper. It means a region where the energy is lower than the usual vacuum state, lower than what empty space normally allows. To understand why that is odd, we need to spend a moment with empty space. Empty space sounds like the simplest thing in the world. Nothing there. No air, no dust, no planets, no forgotten socks drifting through the void. But modern physics tells us that the vacuum is not just blank nothingness. It is filled with quantum fields, and those fields are never perfectly still. Even in the absence of particles, there is a restless background of possibility. Empty space as structure, it has rules, it can produce subtle effects. This is strange enough already, because most of us grew up thinking empty means empty, not quietly active in a way that requires graduate-level mathematics to describe. One famous example often mentioned in discussions of negative energy is the Casimir effect. Imagine two very thin plates placed extremely close together in a vacuum. Because of the way quantum fields behave between and outside the plates, a tiny force appears, pressing the plates together. One way physicists describe this is that the energy between the plates can be lower than the energy outside. It is a real, measured effect. It tells us that the vacuum can behave in ways that are not obvious from everyday experience. But the key word here is tiny. The Casimir effect is delicate. It belongs to small distances and subtle laboratory conditions. It is not a cosmic fuel pump. You cannot scale it up casually and wrap a starship in it, any more than you can notice a dewdrop on a leaf and decide to refill the Atlantic by lunchtime. Still, the Casimir effect gives a hint that negative energy-like behavior is not pure fantasy. Nature allows small, constrained examples of something that sounds roughly like what a warp drive might need. That is both encouraging and not encouraging at all, which is a very common emotional state in theoretical physics. Encouraging because the concept is not meaningless. Not encouraging because the amount, arrangement and stability needed for a warp bubble are of a completely different order. It is like learning that a child can blow a soap bubble and then asking whether the same method can build a transparent dome around Jupiter. The problem is not only quantity, it is also arrangement. The warp bubble would need exotic energy placed in a very particular shape around the ship. The front and back of the bubble do different things. The space-time ahead must contract. The space-time behind must expand. The middle must remain safe. The boundary must hold together. That means the energy cannot simply be dumped into a tank. It has to be distributed with astonishing precision. A rocket engine can burn fuel and throw exhaust backward. A warp drive, if it could exist, would need to sculpt the gravitational behaviour of space-time itself. It would be less like lighting a fire and more like persuading the universe to fold one very specific origami shape while the paper is made of reality. Negative mass is another idea that often appears near this conversation, though it must be handled carefully. Negative mass would be matter that responds to forces and gravity in unusual ways. In everyday life, mass is always positive. Push a shopping trolley, and it accelerates in the direction you push, unless one wheel is determined to ruin your afternoon. Positive mass attracts other positive mass gravitationally. It behaves in the familiar manner that allows planets, stars and people to exist without flying into conceptual confusion. Negative mass, if it existed, could behave very differently. It might accelerate in the opposite direction from a push. It might gravitationally repel ordinary matter or create strange runaway effects when paired with positive mass. That sounds wonderfully useful for science fiction, but nature has not handed us confirmed chunks of negative mass. There are systems in condensed matter physics where effective mass can be negative in a limited technical sense, meaning particles or excitations behave mathematically as if they have negative mass within a material. But that is not the same as having a block of true negative mass matter floating in space, ready to be loaded into a warp core. Effective behavior inside a special medium is not a bucket of exotic matter for bending space-time. It is a useful analogy, and sometimes a powerful laboratory tool, but not the ingredient the Alcubierre drive appears to need. The distinction matters because popular discussions can easily blur these ideas together. Negative energy, negative mass, exotic matter, vacuum energy, antimatter, and dark energy can start to sound like different labels for one mysterious cosmic substance. They are not the same. Antimatter, for example, is real and has positive mass. It behaves gravitationally like ordinary matter as far as current evidence indicates, and when it meets matter, both can annihilate into energy. That makes antimatter extremely energetic, but it does not make it the negative energy needed for an Alcubierre bubble. Dark energy is the name we give to whatever is causing the accelerated expansion of the universe, but it is spread thinly across space and is not something we know how to bottle, steer, or use to make a compact warp bubble. Vacuum energy is tied to the quantum fields of empty space, but its relationship to gravity is one of the deepest puzzles in physics. All of these ideas are strange, but strange in different ways. So when we say the warp drive needs exotic energy, we should not imagine a single known substance waiting for a better mining operation. We are talking about a requirement that points beyond known engineering, and perhaps beyond known physics. The energy must have the right gravitational effect. It must violate certain ordinary expectations about matter and energy. It must be shaped around the ship. It must remain stable. It must not destroy the ship, the destination, or the concept of a pleasant afternoon. In general relativity, there are conditions that ordinary matter usually obeys. They are called energy conditions, though we do not need to list them like a tired textbook. The idea is simple enough. Ordinary matter tends to have positive energy density. It behaves in ways that make gravity attractive overall. These conditions help keep spacetime from doing too many wild things, like forming time machines, wormholes, or warp bubbles whenever someone has a complicated Thursday. But many of the most interesting spacetime shortcuts require violating these conditions. Wormholes need exotic support to stay open. Warp bubbles need exotic energy to take their unusual shape. The universe seems to allow the equations to imagine such things, then asked for a payment in a currency we may not possess. This payment is the price of bending reality. Not money, not fuel alone, but access to forms of energy that do not behave like the matter around us. If ordinary rockets are expensive because they need huge amounts of propellant, warp drives are expensive because they need the universe to provide a rare kind of gravitational behavior. It is the difference between asking for a large meal and asking for a meal made of ingredients that may not exist in the kitchen. Early estimates for the energy required by the Alcubierre drive were staggering. Some versions suggested amounts comparable to enormous cosmic objects. Later researchers explored modified bubble shapes that might reduce the requirement dramatically. This is sometimes presented as if the problem has almost been solved, but that is too cheerful. Reducing a number from absurdly impossible to extremely impossible is still not the same as making it practical. It is good science because it shows the idea can be refined. It also shows that details matter. The shape of the bubble affects the energy demand. A thinner bubble wall, a different geometry, or a smaller region can change the calculation. But even the more optimistic versions remain far outside anything we know how to build. There is also a trap in focusing only on total energy. People like big numbers, especially in space topics, because they make the imagination sit up straighter. But the type and distribution of energy may be even more important than the total amount. If you need negative energy arranged around a bubble wall, then having a large amount of ordinary positive energy does not solve the problem. A warehouse full of bricks does not help much if the recipe requires smoke shaped into a staircase. You need the right ingredient, in the right form, in the right place, behaving in the right way. And then there is stability. Suppose a civilization somehow produced enough exotic energy. Could it hold the bubble steady? Spacetime is not a passive material waiting to be moulded without response. The bubble would interact with fields, particles, radiation, and perhaps its own gravitational effects. Small disturbances might grow, the boundary might wobble, the ship might be exposed to tidal forces or radiation. The very exotic energy needed to create the bubble might be limited by quantum rules that prevent it from lasting long enough or being concentrated enough. Quantum theory often allows strange things, but it tends to attach fine print. Tiny unusual effects may be permitted for tiny intervals or tiny distances, while large sustained violations may be forbidden. The universe is very good at offering a hint and then taking away the ladder. This is one reason some physicists suspect that practical warp drives may be impossible even if the mathematical solution exists. The equations of general relativity can describe a space-time shape, but not every described shape can be produced by physically reasonable matter. It is like drawing a bridge that floats in midair with no supports. The drawing can be precise, the geometry can be elegant, but unless materials and forces can actually hold it, the bridge remains a drawing. The Alcubierre bubble may be a beautiful bridge in space-time, but the supports appear to be made of exotic energy, and we do not know whether nature manufactures enough of it or any usable form of it at all. There is also the unsettling possibility that trying to create a warp bubble would create other disasters. Energy concentrated in the bubble wall might generate intense gravitational effects. Particles caught at the front could become dangerously energetic. Radiation could build up. The bubble could produce horizons, regions that block signals, making control difficult or impossible. If the exotic energy arrangement failed, the bubble might collapse. What happens then depends on details we cannot test, but collapse of a highly curved space-time geometry around a ship is not the sort of event one wants to experience without reading the safety instructions first. The phrase negative energy can also make the concept sound like it would repel gravity in a simple and useful way. But gravity in general relativity is not just a pull, it is the curvature of space-time caused by energy, pressure, momentum and stress. Pressure itself can gravitate, energy flow matters. The geometry needed for warp travel is not just a matter of placing some repulsive stuff behind the ship and some attractive stuff in front. It is a detailed arrangement of space-time curvature. This is why the problem is so hard. The universe is not a toy magnet set. You cannot simply put blue gravity over here and red gravity over there and expect Alpha Centauri to appear by tea time. Yet the difficulty is also what makes the idea scientifically valuable. Exotic energy is not merely a barrier in the story. It forces us to ask what the vacuum really is, what quantum fields allow, how general relativity and quantum mechanics fit together, and whether space-time shortcuts are physically meaningful or only mathematical mirages. A warp drive may never be built, but studying why it is hard leads directly into some of the deepest unresolved questions in physics. The dream points toward the foundations. This is a pattern that appears often in science. A dramatic idea asks for impossible ingredients. Researchers study the ingredients and learn something useful, even if the original machine remains impossible. Alchemy did not turn lead into gold in the old dreamlike way, but it helped lead toward chemistry. Perpetual motion machines do not work, but thinking carefully about why they fail sharpened our understanding of energy and thermodynamics. Warp drives may never cross the stars, but the question of what energy conditions allow may teach us something real about space-time, quantum fields, and gravity. There is a calm honesty in saying that. A scientific dream does not need to be close in order to be worth thinking about. It only needs to be clear enough to teach us where the mystery lies. The Alcubierre drive does that very well. It says, here is a shape of space-time that would behave like faster-than-light travel without locally breaking the speed limit. Then it says, to make this shape, you appear to need exotic energy. Then the universe folds its arms and waits to see what we do next. What we do next, at least for now, is not build one. We examine, we calculate, we test small quantum effects, we study gravity with better instruments, we observe black holes, neutron stars, gravitational waves, and cosmic expansion. We try to understand whether the vacuum has usable structure, or whether negative energy is forever trapped in tiny constrained phenomena. We ask whether alternative warp geometries reduce the requirements, whether quantum inequalities forbid the needed arrangements, whether causality imposes a final no, and whether a future theory of quantum gravity will close the door or open it in a way we cannot yet imagine. The price of bending reality may be too high. It may not be high in the sense of difficult but possible. It may be high in the sense that the currency is fictional. That is the sober possibility. nature may simply not allow stable, large, controllable negative energy distributions. It may protect causality and space-time from being shaped into shortcuts. The Alcubierre drive may remain a carefully described impossibility, a lesson in what relativity can write down but physics cannot build. But there is another possibility, more modest than fantasy and still deeply interesting. Perhaps studying these ideas will reveal that the original version is impossible, but that our understanding of space-time can be expanded. Perhaps the future will not bring a classic warp engine, but new ways of using gravity, quantum fields, or space-time geometry on smaller scales. Perhaps the dream of crossing stars will be served by other technologies, slower but real, while the Alcubierre drive remains a lighthouse for imagination. Or perhaps, very far ahead, a civilization with knowledge beyond ours may find that the universe's restrictions are not quite where we thought they were. Not broken, not ignored, understood more deeply. For now, exotic energy is the gatekeeper. Negative mass remains hypothetical. Negative energy appears only in tiny quantum whispers, not in the grand, obedient oceans a warp bubble would need. The ship in the middle can be imagined, the space in front can be drawn as contracted, the space behind can be drawn as expanded. But the boundary, the actual physical shell of warped space-time, asks for a kind of matter and energy that sits beyond our reach. That is the price. Not just power, but strangeness. Not just fuel, but a new command over the vacuum itself. And so the Alcubierre drive becomes both more beautiful and more difficult at once. The dream survives because the mathematics gives it a shape. The doubt survives because the energy demands refuse to become ordinary. Between them lies the real scientific tension. Not a simple yes, not a simple no, but a careful question waiting at the edge of known physics. If space-time can be bent, what can bend it in exactly the right way? If the vacuum is not empty, can it ever be engineered? If negative energy exists only in faint and limited traces, can those traces tell us something about the deeper rules that hold the universe together? These questions do not yet carry a ship to the stars, but they do carry the mind toward the next problem, the one that asks whether a warp bubble could ever step out of mathematics and become something more than an elegant shape on the far side of possibility. The strange thing about the Alcubierre drive is that it already exists in one sense, and does not exist at all in another. It exists as mathematics. It exists as a carefully described shape of space-time, a solution that can be written down and studied and argued over by people who enjoy putting the universe under a very bright lamp. But it does not exist as a machine. There is no warp bubble humming quietly in a laboratory. No small test craft has vanished from one side of a room and appeared at the other, while the researchers pretended not to look too excited. No engineer has tapped a glowing ring around a spacecraft and said, well, it only bends reality a little, but it should pass inspection. The Alcubierre drive remains a bridge made of equations, and the great question is whether that bridge could ever be built out of physics. This is an important distinction, because mathematics is powerful, but it is not the same as permission from nature. Mathematics can describe many worlds, many shapes, many possibilities. Some are physically real, some are useful approximations, some are beautiful but impossible. You can draw a staircase that climbs forever, but that does not mean a carpenter can build it. You can imagine a perfectly frictionless surface, but your kitchen floor will still find a way to betray you if you wear socks too confidently. In physics, an equation can point towards something real, or it can reveal the boundary between what can be described and what can actually happen. The warp bubble sits exactly at that boundary. General relativity, Einstein's theory of gravity and space-time, allows us to describe curved geometries. It tells us that matter and energy shape space-time, and that space-time guides the motion of matter and light. Within that language, Alcubierre found a way to describe a bubble that could carry a ship across distance in a way that looks faster than light from far away, while the ship itself remains locally within the rules. That is the mathematical existence of the drive. It is not fantasy in the loose sense. It is not just someone saying, imagine if space did a flip. It is a structured idea inside a serious theory. But once the idea is written down, the universe begins asking follow-up questions. What produces this space-time shape? What kind of energy creates it? Where does that energy come from? Can it be arranged around a ship? Can it be held steady? Can it be started and stopped? Can it avoid forming horizons that prevent control? Can it avoid blasting the destination with dangerous radiation? Can it preserve causality, the quiet rule that causes should arrive before their effects? These questions are where the dream begins to feel less like a door and more like a hallway full of locked doors, each one with a physicist standing beside it, politely asking for evidence. The first and most famous obstacle is still the need for exotic energy. A warp bubble is not a simple curve like the one made by a planet. It has a very specific shape. The space in front must contract. The space behind must expand. The middle must stay calm enough for a ship and its passengers. To make space-time take that shape, the original Alcubierre model required negative energy density, the kind of thing ordinary matter does not provide. This is not a small engineering inconvenience. It is not like needing a stronger alloy or a better cooling system. It is more like needing a kind of gravitational ingredient we have only seen hinted at, in tiny quantum effects, and never in the vast, stable, controllable form a warp bubble would require. Some later studies tried to make the problem less severe. Researchers explored different bubble shapes and showed that changing the geometry might reduce the amount of exotic energy needed. That is worth noting because it means the original terrifying energy requirement was not necessarily the final word. The shape of the bubble matters. A wider bubble, a thinner wall, a smoother transition, all these details can change the calculation. Physics is often like this. The first version of an idea may be wildly impractical, then a clever adjustment makes it less wildly impractical. But less impossible is not the same as possible. If the original plan requires a mountain of diamonds, and the revised plan requires only a hill of diamonds, you're still not making casual weekend progress. The deeper issue is not only how much energy is needed, but what kind. Ordinary energy is not enough if the bubble demands negative energy in the right places. A future civilization might have access to vast power sources, fusion, antimatter, artificial suns, or technologies we cannot imagine. But power alone does not solve a problem of sign and structure. If the geometry requires negative energy, then more positive energy may simply curve space-time in the wrong way. It would be like trying to open a lock by bringing a larger spoon. The enthusiasm is admirable, but the tool is not right. This is why many physicists are cautious. They are not dismissing the idea because it sounds strange. Physics is full of strange ideas that turned out to be true. They are cautious because the required ingredients may be physically restricted. Quantum theory appears to allow negative energy-like effects in small ways, but it may also impose strict limits on how much negative energy can exist, where it can be placed, and how long it can last. These restrictions are sometimes discussed under the idea that nature may allow brief little debts in energy, but not unlimited cosmic overdrafts. The vacuum may be flexible, but not generous enough to finance a starship. Even if exotic energy could somehow be produced, the next obstacle is shaping it. A warp bubble would need an extraordinary arrangement around the ship. It is not enough to have the ingredient. You need to sculpt it into a dynamic space-time boundary, perhaps surrounding the craft in a shell or field that remains stable as the bubble moves. Imagine trying to arrange fog into a perfect cathedral, then asking it to fly to another star without losing its shape. Now replace the fog with negative energy and the cathedral with curved space-time, and the problem becomes only slightly less suitable for a relaxing evening hobby. Control is another problem, and it is one of the most unsettling. A normal vehicle can be steered because signals from the driver reach the engine, the wheels, the wings, or whatever part is doing the guiding. In a warp bubble moving faster than light relative to distant space, the front edge of the bubble may be causally cut off from the ship inside. That means a command sent from the ship might not be able to reach the leading boundary. If the crew cannot influence the front of the bubble, then steering becomes difficult to define. The passengers might be safe in the middle, but safety is not the same as control. A train without controls inside is still a train, but it helps if someone sensible is deciding where the track goes. This raises the possibility that a warp bubble, if physically possible at all, might not function like the starships we imagine. It might need to be created by external machinery. It might require a prepared route. It might need devices at the starting point and destination. It might be more like opening a controlled space-time corridor than turning on an engine. This is less romantic than a captain giving a command and crossing the galaxy before the tea cools, but science has a habit of being less cinematic and more complicated. The real future, if it ever contains any version of warp travel, may look nothing like the clean dramatic leap of fiction. Then comes the question of stopping. Starting a warp bubble is already hard enough, but stopping it may be just as mysterious. If the bubble is a self-contained distortion moving through space-time, how does it slow down? How does it release the ship into normal space? How does it avoid dumping accumulated energy forward at the destination? If particles and radiation gather at the leading edge during travel, stopping could unleash that energy. A journey that ends with a dangerous burst would not be a triumph of exploration. It would be more like knocking on the door of another star system using a hammer made of lightning, which is rarely considered polite. Radiation hazards are not a minor detail. Space may seem empty, but it contains enough particles and light to matter when travel becomes extreme. A warp bubble crossing interstellar distances might interact with those particles in ways that concentrate energy. Light from ahead could be shifted to higher energies. Dust grains could become dangerous. The front edge of the bubble might become less like a windshield and more like a cosmic collection point for trouble. Any real design would have to answer this carefully. It is not enough to arrive quickly. One must arrive without turning the arrival into a physics demonstration nobody survives. There is also the issue of horizons. In relativity, horizons are boundaries beyond which signals cannot reach certain observers. Black holes have event horizons, the famous invisible borders from which light cannot escape outward. A warp bubble may produce horizon-like features of its own, depending on its speed and shape. These horizons could prevent communication with parts of the bubble and complicate control. They could also produce quantum effects, perhaps radiation or instabilities. Once horizons enter the story, the mathematics becomes deeper and the comfort level of engineers generally decreases. Causality remains perhaps the most serious philosophical and physical concern. Faster than light travel, even by clever space-time geometry, can sometimes be arranged in thought experiments to create closed loops in time. That means, in principle, a traveller or signal might return to an event before it left. This threatens the order of cause and effect. Physics does not like paradoxes. It may tolerate strangeness. It may allow particles to behave as probability waves and black holes to hide entire histories behind horizons. But letting someone send a message to their own past and prevent the message from being sent in the first place is the kind of thing that makes reality look untidy. Many physicists suspect that deeper laws prevent such situations. Maybe warp bubbles cannot be arranged in causality-breaking ways. Maybe quantum effects destroy them before they become time machines. Maybe a complete theory of quantum gravity will close the loophole entirely. We do not know. This is why the question, could a warp bubble ever become more than mathematics, does not have a simple answer. The honest answer is not yes. It is also not a casual no. It is more like, the mathematics exists, but the path to physical reality is blocked by several enormous unknowns. Some may be engineering problems in the extremely distant future. Some may be fundamental impossibilities. We do not yet know which is which. That uncertainty is not weakness. It is the real shape of the frontier. It is useful to compare the warp bubble with other once impossible-sounding ideas. Flight was dreamed of for thousands of years before aircraft existed, but birds were proof that heavier-than-air flight was physically allowed. The moon landing seemed impossible to many people before it happened, but rockets had already shown that the basic principles worked. Nuclear energy sounded almost magical before it became technology. but the atomic nucleus was real and measurable. The warp drive is different. We do not yet have nature's version of a stable warp bubble to point at. We do not see small Alcubierre bubbles drifting around the galaxy like cosmic soap bubbles. We do not possess negative energy in the required form. We have a mathematical possibility, not a natural example. That does not make it worthless. Mathematics often reaches ahead of experiment. Black holes were studied as solutions before they were widely accepted as real astrophysical objects. Gravitational waves were predicted long before they were directly detected. Antimatter was suggested by theory before it was found. But in each of those cases, the theory eventually met observation. For warp bubbles, that meeting has not happened. Perhaps it never will. The task is to avoid both extremes, not to dismiss the idea merely because it is strange, and not to believe in it merely because it is exciting. There are small ways the question could become more grounded. Better understanding of quantum fields might tell us whether useful, negative energy distributions are truly forbidden. A theory of quantum gravity might reveal new constraints on spacetime geometries. Laboratory studies of analog systems might mimic certain mathematical features of curved spacetime, not as real warp drives, but as models that help physicists understand horizons, vacuum effects, and stability. Observations of extreme cosmic objects might teach us more about how spacetime behaves under severe conditions. None of these steps would produce a starship, but science rarely leaps directly from dream to engine. It usually builds a long staircase of less glamorous understanding. A future theory may also change the question completely. The Alcubierre drive is built within general relativity. But we know general relativity and quantum mechanics do not yet form a complete unified picture. At very small scales or extreme energies, space-time may not behave in the smooth way general relativity assumes. It may have quantum structure. It may emerge from deeper relationships. If so, the idea of bending space-time might need to be rewritten. A warp bubble described in smooth space-time could turn out to be impossible in the deeper theory. Or, less likely but more exciting, the deeper theory could reveal new kinds of space-time behavior no one has yet imagined. Either outcome would teach us something. There is an almost humorous humility in realizing how far away the engineering is. To build a warp bubble, one might need to manipulate the vacuum, arrange exotic energy, stabilize space-time curvature, protect the ship from radiation, preserve causality, control horizons, start and stop the bubble, and do all of this while carrying passengers who would probably still complain if the cabin temperature was wrong. It is hard to imagine a more demanding travel technology. Even calling it a technology feels generous. It is more like asking civilization to become fluent in the grammar of space-time. And yet, the history of science warns us not to confuse present difficulty with eternal impossibility. A person living before electricity could not have imagined modern electronics in any practical detail. A person living before relativity could not have imagined satellite navigation needing corrections for time dilation. A person living before quantum mechanics could not have imagined lasers, transistors, or the strange precision of atomic clocks. Future physics may make some of our current impossibilities look naive, but future physics may also confirm that some doors are truly closed. The art is knowing the difference, and we do not know it yet. For the Alcubierre drive, the most reasonable attitude is careful wonder. Wonder, because the idea is genuinely beautiful. It takes the speed limit seriously and still finds a new question hiding beside it. It treats space-time as active rather than passive. It turns the dream of reaching the stars into a problem of geometry. Careful, because every known path from equation to engine runs into exotic energy, stability problems, control issues, radiation concerns, and causality questions. A warp bubble may be allowed in the loose mathematical sense, and forbidden in the deeper physical sense. Or it may be possible only under conditions so extreme that no civilization could ever use it. Or it may point towards some future insight that changes the way we think about travel, without producing the classic warp drive at all. There is also a human reason to keep asking. The stars are too far away for ordinary ambition to feel satisfied. We can send probes, we can improve rockets, we can build telescopes that look across cosmic time, we can listen, measure, and imagine. But the dream of crossing the distance remains. The Alcubierre bubble gives that dream a disciplined shape. It says, do not simply wish for speed. Ask what speed means. Ask what distance means. Ask whether the structure of space-time contains possibilities that ordinary motion does not. Even if the answer is no, the question itself sharpens our understanding. This is what separates serious speculation from empty fantasy. Serious speculation carries its own doubts. It names its obstacles. It does not hide the impossible parts behind shiny words. It says, here is the idea, here are the equations, here is the required energy, here are the reasons it may fail. The Alcubierre drive survives in scientific conversation, not because it is likely to be built soon, but because it is precise enough to be challenged. And in science, being challengeable is a kind of respectability. A vague dream floats away. A clear idea can be tested by thought, calculation, and eventually perhaps by experiment. So could a warp bubble ever become more than mathematics? Perhaps. But not by simply building a stronger engine, not by adding more fuel, not by ignoring the speed of light. It would require a revolution in our ability to understand and manipulate space-time, a command of exotic energy we do not possess, and answers to problems that currently sit like mountains around the concept. It would require nature to be more permissive than many physicists suspect, and civilization to become more capable than we can easily imagine. That is a very narrow bridge between dream and reality, and at the moment, we do not even know whether the bridge has foundations. Still, the bubble remains in the mind, a small, calm region surrounded by impossible geometry, a ship that does not race, yet arrives, a mathematical island at the edge of relativity. It may never lift into reality. It may remain a beautiful warning about the difference between equations and machines, but it also reminds us that the universe is not exhausted by our current tools. There are questions we can barely ask, and some of them are worth asking slowly, carefully, even if the answers are far beyond us. For now, the Alcubierre drive belongs to that twilight place between physics and possibility. It is not a promise. It is not a plan. It is not a secret technology waiting just out of sight. It is a question shaped like a spacecraft and written into the language of curved space-time. Whether it will ever become real depends on things we do not yet understand. The nature of the vacuum, the limits of negative energy, the rules of quantum gravity, and the deep protection of cause and effect. And even if the final answer is no, the journey through the question leaves us with something valuable. It shows us that faster than light travel is not merely a matter of going faster. It is a way of probing what space is, what time is, and how far the universe allows imagination to walk before the laws of nature gently ask it to stop. That is where the Alcubierre drive becomes more than a machine, even without becoming a machine at all. It becomes a mirror held up to our future. It reflects our impatience with distance, our respect for physical law, and our strange willingness to dream inside the boundaries of what may be impossible. And as we turn toward the final part of this journey, the question changes again. Not just could we build such a thing, but what does the idea reveal about us, about space travel, and about the long future of a species that looks at the stars and still wonders whether the road between them might one day bend? The Alcubierre drive whispers something very unusual about the future of space travel. It does not whisper that starships are waiting just around the corner. It does not whisper that we are one clever engine design away from breakfast on Earth and supper around another sun. It does not even whisper that faster than light travel will definitely happen. Its message is quieter than that, and perhaps more interesting. It says that the future of space travel may not only depend on building better machines. it may depend on understanding space itself so deeply that the word travel begins to change its meaning. That is a strange thought, because for most of human history, travel has meant crossing a distance by moving through it. You walk across a field, you sail across a sea, you fly across an ocean, you launch a spacecraft across the empty dark between worlds. The method changes, but the idea feels familiar. There is a place here, a place there, and a stretch between them that must be crossed. The Alcubierre drive asks whether the stretch itself is part of the problem. It asks whether the deep future of exploration might involve not simply moving through the universe, but learning how the geometry of the universe can move, stretch, contract, or guide motion in ways our current technology cannot touch. That does not make it a practical blueprint. It makes it a signpost. A strange one perhaps, leaning at the edge of known physics with a note attached saying, "The road may not be what you think." And that matters, because space is not just far, it is discouragingly far. Even the solar system, our own small cosmic neighbourhood, is large enough to humble every engine we have ever built. A trip to Mars can take months. A trip to the outer planets can take years. The nearest stars are so distant that ordinary travel begins to feel less like a journey and more like a commitment made by many generations of people who have agreed to be patient on a scale most of us reserve only for waiting rooms and software updates. So the future of space travel may unfold in stages. The first stage is not warp drives at all. They are better rockets, better life support, better radiation shielding, better navigation, better habitats, and better reasons to go. Human beings may return to the moon. We may build stations in lunar orbit or bases on the surface. We may send people to Mars slowly and carefully, with all the caution required when the destination is a cold desert millions of miles away, and the return trip is not exactly a taxi ride. We may explore asteroids, icy moons, and the outer planets with machines long before people follow. These are real steps, not glamorous shortcuts. They are the slow, hard work of becoming a spacefaring species. And in that slow future, the Alcubierre drive remains far ahead, almost like a dream seen through a telescope. It does not replace near-term space exploration. It does not solve the engineering problems of rockets, fuel, food, shielding, or human health in space. If anything, it reminds us how much we still do not know. We cannot build a warp bubble while we are still learning how to keep astronauts safe beyond low Earth orbit for long periods. We cannot bend spacetime on command while ordinary spacecraft still require careful launch windows, delicate trajectories, and a great many people staring at screens with the calm expression of those who know one loose bolt can ruin a century of ambition. But dreams have their place. They give direction to curiosity. They stretch the imagination beyond the immediate checklist. The Alcubierre drive is not useful because it gives tomorrow's engineers a simple design. It is useful because it points to the deeper physics that any truly advanced spacefaring future may need to understand. It points to gravity, quantum fields, vacuum energy, causality, and the structure of space-time. These are not decorative mysteries. They are the foundations underneath every possible path to the stars. Imagine a civilization thousands or millions of years ahead of us, not in magic, but in knowledge. Such a civilization might look back at our current rockets the way we look at early wooden boats, brave, clever, and limited. They might not think of space travel as simply throwing a vehicle through emptiness. They might think in terms of fields, geometry, gravitational structure, and energy arrangements we have no language for yet. Perhaps they still would not have warp drives. The laws of physics may forbid them. But they would understand why with a clarity we do not have. And if there are other paths through the same deep terrain, they would see those paths before we could. That may be the most honest promise of the Alcubierre drive. Not that it will become real, but that it teaches us where to look. It tells us that the barrier between stars is not only technological, it is conceptual. We need to understand what space is. We need to understand whether the vacuum can be engineered, whether negative energy is truly limited, whether quantum gravity reshapes the rules, and whether the speed of light is guarded in ways deeper than relativity alone shows. These are enormous questions. They may not produce a warp engine. They may produce something more valuable, a better understanding of reality. There is also a practical humility hidden in the idea. Science fiction often imagines faster than light travel as a convenience, the tool that lets stories move quickly from one star system to another without making everyone wait centuries between scenes. Real physics is much less accommodating. It does not care about pacing. It does not care whether the nearest interesting planet is too far away for a neat plot. The Alcubierre drive, even in its most hopeful form, is not simple convenience. It is a reminder that if faster than light travel is possible at all, it will likely be tied to some of the hardest problems in physics. It will not be easy. It will not be cheap. It will not be a matter of installing a bigger engine and hoping the universe looks the other way. And perhaps that is a good thing. The difficulty gives the dream weight. If the stars were easy to reach, we might take them less seriously. The vastness of Space Force's patience, cooperation, and humility. It asks us to think not only about how to go, but why. What would we carry with us? What kind of species would we become on the way? Would we cross space as careful explorers, or as impatient tourists dragging our problems from one world to another? A warp drive, if it ever existed, would not just be a machine, it would be a responsibility. Any technology that can reshape space-time, cross interstellar distances, or disturb the environment around another star would demand wisdom, at least as advanced as the physics behind it. And wisdom, as history gently reminds us, is not always delivered at the same time as engineering. Even slower space travel raises these questions. A generation ship, travelling below light speed, would be a world in miniature. Its passengers might live and die between stars. Their descendants might arrive at a destination chosen by ancestors they never met. A tiny robotic probe pushed by light could reach another star far sooner, but it would carry no people, only instruments and memory. Suspended animation, if it ever became possible, would change the meaning of a long journey. Artificial habitats might make the destination less important than the voyage. Each possible future asks what it means to travel when the distances are larger than a lifetime. The Alcubierre drive enters this conversation as the boldest possibility, not because it is nearest, but because it challenges the very tyranny of distance. If warp travel remains impossible, humanity may still reach outward. We may become patient. We may send machines first, then perhaps settlements, then perhaps self-sustaining habitats that do not need planets at all. We may learn that the future of space travel is not about rushing from star to star, but about expanding slowly, carefully, and sustainably through the places we can actually reach. That future may sound less dramatic than a warp jump, but it is still extraordinary. A civilization that can live beyond its birth world has already crossed a profound threshold. It has learned to carry Earth not as a place, but as knowledge, biology, culture, and care. The Alcubierre drive also whispers that imagination should remain disciplined. It is easy to say, one day we will figure it out, and leave the hard parts in a pleasant fog. But science is at its best when wonder and honesty sit together. The honest part says we do not know how to create the exotic energy required. We do not know whether negative energy can exist in the needed amounts. We do not know how to stabilize a bubble, steer it, stop it, or prevent dangerous effects. We do not know whether causality would allow such travel at all. The wonder part says, and yet the mathematics showed us a new way to ask the question. The two belong together. Wonder without honesty becomes fantasy. Honesty without wonder becomes a locked room. This is why the Alcubierre drive continues to fascinate physicists, writers, engineers, and tired people listening late at night. It lives in that narrow band between impossible and not yet fully understood. It does not offer comfort in the form of certainty. It offers comfort in the form of curiosity. It shows that even the limits of the universe can be explored with care. The speed of light is not merely a wall that stops thought. It is a clue to the deeper structure of space and time. When we press against that limit, we learn what kind of universe we live in. There is a similar lesson in the history of flight. People dreamed of flying long before aircraft existed. Many early attempts misunderstood the problem. Some tried to copy birds too literally. Some built machines that could never have worked. But the dream kept people asking questions about lift, air, weight, balance, control, and power. Eventually, the question became precise enough for engineering to answer. The warp drive may not follow the same path. There may be no engineering answer, but it is still helping us sharpen the questions. What is the vacuum? What shapes space-time? What forms of energy are allowed? What protects causality? What happens when general relativity and quantum mechanics meet? These are not small questions hiding behind a flashy idea. They're among the deepest questions physics has. Perhaps the future of space travel will be a mixture of the practical and the profound. Practical work will build better spacecraft, stronger materials, safer habitats, and more efficient propulsion. Profound theory will continue probing the nature of space-time. The two may seem separate for a long while. One group worries about fuel, radiation, and docking systems. Another worries about quantum fields, negative energy, and the structure of gravity. But history shows that today's abstract physics can become tomorrow's navigation system, medical scanner, or communication network. No one studying relativity at the beginning could have fully imagined the daily importance of precise satellite timing. No one studying quantum mechanics in its early days could have fully imagined the modern electronic world. So even if warp drives never arrive, the physics explored around them may still shape the future in unexpected ways. There is also something deeply human in the fact that we ask these questions at all. We are small creatures on a small planet around an ordinary star, and yet we wonder about bending space-time. We build stories about crossing the galaxy. We write equations about bubbles no one can make. We look at limits and ask whether they are final, or whether they contain hidden structure. This is not arrogance by itself. At its best, it is a form of attention. The universe is vast, and we are trying to understand it, not merely as spectators, but as participants who may one day travel farther than our ancestors could have imagined. Of course, the future may be quieter than our dreams. We may never stand inside a warp bubble. No captain may ever give a calm command while stars bend ahead. The galaxy may remain too large for human bodies to cross quickly. The speed of light may remain not only a limit, but the final keeper of cosmic order. If so, the Alcubierre drive will still have mattered. It will have taught us that even impossible dreams can be scientifically useful when they are shaped with precision. It will have shown us that the road to the stars is not only a road through space, but a road through understanding. And if, in some distant future, a civilization does learn how to manipulate space-time safely, then the Alcubierre idea may be remembered as one of the early questions that pointed toward the door. Not the finished engine, not the final design, just the first clear sketch of a possibility, written by someone who looked at relativity and asked whether the universe's speed limit had a deeper shape. That is often how great changes begin, not with certainty, but with a question that refuses to leave. So what does the Alcubierre drive whisper about the future of space travel? It whispers that the stars are not close, and we should not pretend they are. It whispers that physics is not a set of chains, but a set of truths we must understand before we can move wisely. It whispers that faster travel may require deeper knowledge, not louder engines. It whispers that space is not empty stage scenery, but part of the drama itself, and it whispers that the future, if it is to carry us outward, will need both patience and imagination. We began with a dream of moving faster than light, and found something stranger than speed. We found a bubble of space-time, a ship at rest, a distance reshaped, and a universe that is flexible in theory but stern in practice. We found exotic energy standing like a locked gate. We found mathematics offering a shape while physics asks for a price. We found that the Alcubierre drive is not a promise of tomorrow, but a question for the ages. And now, as this quiet journey comes back to where you are, perhaps in a dark room, perhaps under a window, perhaps with the real stars hidden by clouds or city lights. It is worth remembering that every great voyage begins long before the first vehicle moves. It begins when someone looks at the horizon and wonders whether it is truly the end of the world. It begins when the impossible becomes a question instead of a wall. Tonight, the warp engine remains only a dream written in curved space-time. But dreams like this keep the mind awake in the best way. Not restless, not hurried, just gently open to the size of what we do not yet know. If this journey through warp bubbles, light speed, and the strange patience of the universe has brought you a little calm, I would be ever so grateful if you liked the video, subscribed, or shared this sleepy corner of science with someone else who enjoys wondering quietly about impossible things. And as you settle back into your own small region of space-time, remember that you do not need to cross the galaxy tonight. The stars can wait. The universe has always been patient. For now, it is enough to rest here in this moment, on this turning Earth, while somewhere far beyond us the long road between the stars remains dark, silent, and perhaps not quite as simple as it seems.